Welcome everybody to the second user meeting for PyPSA. So PyPSA is Python for power system analysis, and it's an open source tool for modeling modern energy systems. By modern, we mean with high temporal and spatial resolution to capture the variability of renewables, and also the features to capture all the electrification that we expect in the energy system in the upcoming decades. So I won't say too much more about it. We started it 8.5 years ago now, and we're always kind of surprised and gratified how many users are using it. And we organize this event to basically get a bit of an overview of what people are doing with PyPSA, also for other potential users, and also give a chance to exchange a bit on how the tool is working and what kind of features might be interesting in the future. So I would really invite all speakers, if they want to make comments in the direction of what they'd like to see in the future, to feel happy to contribute there. I'll say a few thanks right at the beginning as well. Thank you to all of the speakers who agreed to speak today. We appreciate your time a lot. And a big thank you to Bobby Xiong and Kasper Schaus for organizing everything. And with that, I'd hand over to you two.
Thank you very much, Tom, for the kind words and the introduction. Yeah, we'll have some introductory words on the organizational side before we dive into the discussions and the lightning talks in a few minutes. Just going to quickly share the screen. Can you see it?
Yeah.
Perfect. So welcome also from our side. Kasper and I will be moderating throughout the day, and also give some insights or some insights around the format. So the speakers already know we'll have 8 to 10 minutes lightning talks, and we would kindly ask you to stick as close to the 8 minutes as possible. So any delay will not add up in the 3 hours of presentations that we will have today. At around minute 9, we'll give you a kind reminder, but at minute 10, we would need to stop and cut off and move to the Q&A session, which will take around 3 minutes. We will then transition smoothly to the next speaker. For the audience, we will also kindly ask you to keep your microphones muted, and feel free during the lightning talk to post your questions into the chat. We will collect them and then select 1 to 3 persons to elaborate their questions after the talk, depending on how much time we still have left after the lightning talk. And all unanswered questions can still be addressed either in the chat room or also in the breakout sessions. And you're also welcome to connect, of course, afterwards with the authors and amongst all and everyone in the audience. As mentioned, the meeting will be recorded and shared then afterwards on YouTube, so we can make it available to the entire community. We have a quick overview on the 2 sessions. We split it in 2 halves. We'll start with 6 talks, the first one by Tom Adams, then followed by Malcolm, Tapio, Andrew, Agnès, and Peter, on different applications, of course, of PyPSA. Then we will have a 10-minute break. The times are indicative, so it could be that we move it by a few minutes, depending how good we are on the timekeeping. The second half will be similar, 1 more talk. So we'll have 7 talks in total for the second half by Marta, Ganesh, Carlos, Rowan, Tom, Sean, and Adrian. We'll then conclude and move into the optional breakout sessions. Of course, everything is optional today, but you're welcome to stay longer to discuss and exchange freely in the 3 breakout rooms that we have organized. So we are also very interested, of course, in your feature requests, apart from what you are doing already with PyPSA. We keep improving the model and the framework. So we are very keen on knowing what features you would like to see in the future. This first room will be moderated by Fabian Neumann. The second room will tackle the topic of country case studies. We will have many case studies for different regions all around the world today. This will be moderated by Max Parsen and the PyPSA-Earth group. And feel free to exchange here on country-specific use cases and also best practices. And then last but not least, we have a third room on sector coupling and power to X, which will be moderated by Kaspar Schaus, where you can exchange freely on sector coupling. Just a final remark on this side, the breakout sessions will not be recorded, and you are also free to select the breakout rooms of your interest yourself. You can freely discuss, and of course, as mentioned, you're invited to connect with other users. All right. So without further ado, we would then start the lightning talks with Tom Adams from Haast Energy being the first speaker today. And I think time-wise also the furthest apart. So you will, Tom, you're from Haast Energy, a boutique trading firm with a focus on wholesale electricity and gas markets in the APAC region and based in Auckland, New Zealand. And your approach is to use quantitative models to understand market fundamentals and price formations. We're very excited on your lightning talk about modeling security constraint dispatch in the Australian grid. The floor is yours. You are free to share the screen.
Cool. So this is a quick talk on modeling the Australian national energy market, the NEM. Just a quick overview of who Haast Energy trading is. I put please draw an annotated infographic about Haast Energy trading into ChatGPT, and they say a picture says 1,000 words. Most of these aren't even words, but yeah, I think we maybe are in the minority of PyPSA users because we're very short term. We're not looking at infrastructure change. We're interested in energies and energy prices and flows in the range of a few weeks to maximum a couple of years. We are obviously interested in if there is going to be some infrastructure change brought about by somebody else. We have a very, I think, quite small precise usage of PyPSA compared to some of the more broader research topics. However, I'm definitely really keen to reach out to anybody else who's doing this kind of thing with PyPSA, share some ideas. So I've put my email address at the start and the end. Because it is very early in the morning here, I'll stick around until the first breakout, but I might watch some of the later talks in the recording because it is very early in the morning here. So the Australian NEM, there is electricity in Perth, just to be clear. It's just on a different grid. The NEM covers 5 states, ACT as part of ACT is part of New South Wales, and there's one price per state. Fairly typical is interconnectors connecting states, and dispatch is centralized and based on minimizing total cost. There are energy reserve markets, all that usual kind of thing. There are constraints that control dispatch, and these constraints are provided by the transmission providers. They use all sorts of things to model it based on their knowledge of the grid with the various details about capacitance and inductance, etc. Last time I checked a few days ago, there was 500,000 constraints or thereabouts, and there's more and more every day because there needs to be a constraint. Lots of constraints, not only for system normal, but anytime you take one line out or one piece of infrastructure out, you need a whole lot of new constraints to cover that. And then when you have a combination of outages, a new set of constraints for that. So my point here is it's impossible for us to replicate. It requires too much knowledge, too many systems we don't have access to. But if we're trying to model the grid, could we use PyPSA as a bit of a shortcut? And thermal constraints, just looking at the marginal value, have double the impact of any other sort of constraint. There's a lot of information online about thermal line ratings, etc. in Australian NEM. So the talk here is our attempts to use PyPSA to model specifically those thermal constraints and hope that the rest are negligible enough that we get a reasonable answer just looking at the thermals. Here's a classic example in the Australian grid. There's a whole lot of solar in Western New South Wales. And we call these 051 constraints because this is one high capacity line here, the 051, that runs in parallel with a series of smaller low capacity lines. So during the middle of the day, all that solar in Western New South Wales wants to go east to the price node in Sydney. Obviously, if that high capacity line trips, then that power will be forced into these lower capacity lines, which could overload them. So in fact, what you see often is despite one high price at the price node in Sydney and a lower price in Melbourne, the power is actually being forced south against the price gradient, which is obviously not what an efficient grid should do. But it's exactly the sort of thing we want our modeling to demonstrate. So to build the model, we used a range of AMO data, which is the market operator in Australia, and other sources. A moderately large size model with about 400 buses, and adapted the security constraint for line security. We haven't done generator security, just n-1 line security, which means the system is still secure if one line goes out somewhere. And in the NIM, the generator bids and offers, which we need for marginal prices, are made available next day. So we could run some tests using that. Each generator gets 10 offers, a certain amount of megawatts for a certain price. So you can obviously create a bid stack there. Just to be clear, the NIM dispatch itself, called NIMD, the NIM dispatch engine, only has 5 nodes. Constraints capture the complexity around all of the many buses within each node, but they're not. Each bus isn't inherently modeled in NIM. It just has the constraints, which means that the constraints, as I said, are calculated externally, don't update with the network. So, for example, with this new interconnector being built here between South Australia and New South Wales, there will need to be a whole lot more constraints for that, versus in PyPSA, where we have 400 nodes. The constraints are calculated internally and update as we change the network. So just out the box, the 051 constraints have the correct diurnal pattern, which is great. And in this example here, we see exactly what we hoped, power flowing south from high price to low price, as it should. And if we look at a time series of some prices and interconnector flows, particularly look at the interconnector flow, we can see we haven't quite captured all of the detail. But we've got the general shape right of prices and interconnector flows, which is a great start. And for us trying to model things around the network, it's nice to see. Extensions to this, well, this dotted line here is a brand new interconnector between South Australia and New South Wales that's being built. What happens when we put that in? Australia is in the middle of a large energy transition from coal units to renewables. So a lot of units being shut down or new generation being opened up, and a whole lot of new lines and interconnectors to connect that. But even more short-term, pragmatically, there is always going to be a combination of outages that is coming up in the future that hasn't happened before. So how can we model, how will the model perform on those kind of things? Issues we have for predicting bids and offers is really hard. I've shown you just using actual bids and offers, but it's pretty hard to pick them. Not impossible, pretty tricky to pick them in the future. As I mentioned, all those non-thermal constraints as well. And we've had a bit of a go at including losses. In Australia, they get negative prices that will go down to minus $1,000. And if you have a negative price and you're optimizing dispatch with a loss, it tends to want to create these loop flows that waste as much energy as possible. Thank you very much. As I said, I'm very, very keen to reach out to anybody else who's doing this type of modeling. I'll be here until for the first chat room, for the first breakout. But yeah, please just drop me an email if anyone else is doing this kind of thing. Probably save each other a lot of time. Thank you very much. If anyone's got any questions, let me know.
Thank you very much, Tom, for sharing and also for keeping so well in the time with only 7 minutes. Very exciting, very impressive. Also how close what you have shown the plots were to the real data. We have one question in the room from Tom. Tom, do you want to unmute yourself?
Yeah, I probably have multiple questions, but maybe just one to start with. What adaptations did you have to make to the security constraint OPF? Is there some functionality missing there?
So I mean, the first issue is the fact that it creates every single possible pair of lines it will create a constraint around. So with 800 odd lines, the number of constraints gets so large that it just takes too long to solve. But clearly, there are some lines that are not going to affect another line because they're separated by thousands of kilometers. So there was some diligent pruning of which lines actually can affect each other, and reducing the number of constraints was a big one.
I think though you can give it a list of the lines that you want to participate in the security constraint. No, it doesn't have to be all of them. It's you can put a list in basically, but you choose a pruned list basically for the security constraints.
Yep, but even within that pruned list, I didn't want every possible pairwise combination.
Okay, I understand. Yeah, that makes sense for a long. Yeah, I understand what you mean now. Sorry, yeah.
Yeah, obviously, there'll be some lines down here in Adelaide that are relevant to each other and not relevant, up in Cairns. They are needed to be included, but not the combination between them. And generally, the number of lines that could trip is going to be shorter than the number of lines that they could affect. I'm not too worried about a very low voltage line tripping. I am worried about the effect on it. But yeah, the adaptations were predominantly around speed.
But maybe we can. I don't know if it makes sense to try and make that kind of pruning easier in the code or not. If you have any nice way of doing it, then tell us, and we can put that into the code.
A lot of it I've done around looking at the size of the impact relative to the rating of the line. First of all, I had to break away from just doing it with one large array, using the one block of constraints for everything. I end up creating a lot of separate constraints, which it's not particularly clean.
Is there any attempt to kind of react to these line failures sort of curatively, where you, rather than trying to preventatively have n-1, you try and react with a storage or something to the line outage? I thought this had been looked into in Australia. I'm not 100% sure though.
Well, I mean, the mid stacks I'm trying to model definitely react to them, which is problematic. But sometimes line outages happen that people don't expect, like when we've had interconnectors blow down, etc. Ultimately, I'm not. Our approach is to try and predict what will happen, as opposed to try and improve what. We're not trying to cure anything. We're just trying to guess what the outcome will be. Definitely, there's a lot of storage in Australia, which in February we had some lines blow down, and they were very useful for that. Our challenge is to try and predict that kind of thing, but we're certainly not telling market operators what they should be doing. We're just trying to guess what they will do.
Thank you.
Yep.
Thank you very much. There's one more hand in, Christian. Yeah.
Yeah. Hello. I wanted to ask. Thank you. Hi. I wanted to ask in your price modeling right now, you have the whole PyPSA network, and how do you aggregate prices to each price area? Do you use the constraints imposed by the TSO, and do you try to model the constraints imposed by the TSO using the PyPSA intermediate data?
Yeah, good question. So in the dispatch itself, there's just one price. There's only 5 nodes. There's only 5 prices, and I do have 372 separate prices. However, the way they deal with losses within each region is to decide that one of these points is the price node, and then losses calculated relative to that in a dispatch engine in a way that's not so applicable here. It's done by scaling prices. So I'm just literally just picking out the prices that are at the regional reference nodes. From all of the many prices that are there, I'm just picking out the ones that are in central Sydney, in central Melbourne, in central Brisbane, because they are the selected reference nodes. There are a whole lot of prices which are very different from that within each state that I just basically ignore. And that is that example where I showed interconnected flows going from high price to low price. Actually, if you looked at the price nodes either side of the interconnector, it would have been going from low to high, relative to the reference nodes, it was going from high to low. And that's part of what creates a lot of the dynamics in that at individual nodes, the prices are different to the regional reference node, but the generators are being paid by the reference node, but not by their own price. So no complex aggregation, just picking the relevant ones.
Right, thanks.
Right. Once again, thank you, Tom and Christian, for the question. We would then directly smoothly move on with the second talk by Malcolm Moss from Virginia Tech. He's an entrepreneur and business owner, loves analyzing complex systems and understanding the bigger picture. And you hold a degree in computer engineering and will give a talk on applying PyPSA on the ERCOT grid. Also, please feel free to share your screen. The floor is yours.
Okay, hello. Can everybody hear me?
Yes, loud and clear.
Awesome, okay. I think the slideshow should be up now. Yeah, so thank you for the introduction. Really appreciate the opportunity to talk here. I'll be talking about Open ERCOT, my open source grid model for the ERCOT electricity grid. So quick primer on ERCOT. ERCOT covers the majority of the Texas electricity grid. It's sort of relatively isolated within the United States, so it has very little import and export, and is an energy-only market. It has 4 major price nodes, and is essentially, has sort of significant growth over the last couple of years, especially when it comes to renewables and batteries. This project was born out of my capstone project at Virginia Tech. It was inspired by some of my work in power trading, as well as a prior Virginia Tech project that was covering battery energy storage solutions and modeling them and their implications on the grid. We decided to use PyPSA because it's open source and very flexible. We also really like sort of the documentation in some of the community. On the right here, you can see sort of the outline of our model. We've chosen to take the ERCOT grid, which has over 1,000 generators, and map it down to 8 buses. Each of these buses are linked with the sort of the lines you can see on the screen with lossless links. And then each of the different pie charts show the generation capacity on each bus. And the sort of the makeup of each pie chart shows the distribution of generation types within each of them. So one of the biggest challenges within modeling systems within the United States is transmission data. Unfortunately, it's considered to be critical energy infrastructure information throughout the United States, which means that in order to access it, you have to sign non-disclosure agreements. You also have to go through a background check. And essentially, anything that you derive from sort of one-line models or sort of very granular transmission data is very difficult to release to the public. So because we wanted a sort of an open model that used sort of open source data and could be used by other researchers, we chose to sort of map down our system to 8 nodes. On the right here, you can see a paper from back in 2017 that had a similar approach. I think they mapped it down to 15 buses rather than 8. We decided to use 8 because it mapped up much better to the ERCOT load data we had. But essentially, this is something that's been done a little bit before in the literature. I'm not sure if it's been done with PyPSA though. So when we look at our actual model implementation, we were pulling data from 3 major sources. So ERCOT directly, they provided us load data and also some renewable data. We pulled data from the Environmental Protection Agency that gave us very granular data about emissions, which we wanted to analyze for the implications of batteries and their dispatch. And then we also pulled data from the EIA, the Energy Information Administration. They provide very granular data with regard to which units are operating and also which units sort of exist within the grid and where they're physically located. And so our model's relatively simple. We pull down data from each of those sources, we clean it up, we turn it into a PyPSA network, and then we have some tools that sit on top of PyPSA that allow you to sort of fit in a simulation file, which allows you to choose different time periods to dispatch, and then also allows you to change different things like the variable operating cost for different units or the actual transmission constraints between zones. And then we also wrote some tools that can actually look at the outputs and make more interesting visualizations that sit on top of some of the PyPSA visualizations. So when we actually look at some of these outputs that we've created, the first one on the left shows the actual dispatch for a single day within our model. So each of the lines, you can see the direction of flow as well as the size of flow based on the size of the arrow. And then if the line is red, it means we've hit the total transmission capacity of the link. And if the line is white, it means you still have additional capacity left over. You can also see each of the pie charts show the actual dispatch for that specific hour. And the sort of distribution of the pie chart shows the sort of the type of generation. And the size of the pie chart shows the relative quantity of generation in the actual model. And then on the right, you can see the actual monthly generation aggregated up. So we took just the amount generated by each of the different types of generation throughout the month and grossed it up so that you could sort of see differences in load from month to month, as well as the differences in distribution of actual generation. This was helpful for validation and sort of allowed us to see some of the issues that we had with our models and places where we were doing things sort of correctly. So to harken back to what I was talking about earlier, when we originally started this project, we were building on top of a prior project at Virginia Tech that looked at modeling battery energy storage solutions and their implications on the grid. So what we decided to do is we took our model that included batteries, and then we sort of removed them from the PyPSA network and simulated them again. And then we were able to compare the dispatch from year to year. So this covers all of 2022. And then we were able to take each of the individual units and look at their prior emissions rates on a megawatt basis from the Environmental Protection Agency data and actually compare what we thought emissions would be based on sort of our two major simulations. And so sort of the interesting insight that we had was that most of the time, the addition of battery energy storage solutions helps increase the amount of renewables as expected. But because in some months, because we're simulating batteries as purely economic participants, we did actually see increases in emissions. So this could be because of issues with round trip efficiency. We set a 81% round trip efficiency. So if a battery was to charge and increase the amount of non-renewable generation, even if it's economic, it may cause increases in emissions. And so in addition to sort of looking at emissions, we wanted to look at the economic value of each of the different units. This can be seen on the chart on the right. So, through each of the simulations, we took the total LMP payments to each of the units and sort of divided that by their actual megawatts generated throughout the year to essentially give a market value for each different unit. And we wanted to see how the market value of these units changed with batteries and without batteries. And sort of as expected, solar and wind became a little bit more profitable. Nuclear stayed the same, and all other types of generation decreased in their market value. So we thought that was some helpful insight and an interesting analysis that you could do with the model. We think that this model is sort of relatively rudimentary. As an 8-bus system, it's not that granular when you look at the transmission perspective. ERCOT has over 1,500 price nodes and a significant amount of lines that aren't being sort of modeled in this. So the actual understanding of congestion is relatively weak. We also only did this using historical data. We haven't fed in any forecast data into it. We also think there's significant opportunities to look at economic granularity for specific units. So we didn't have any temporal constraints with our model, even though we sort of have them implemented. It just took too long to simulate different startup costs or startup times, as well as ramp rates. So we think that with potentially more economic granularity or more powerful systems for simulation, you could really improve the accuracy of the model. And obviously, we'd love to include more transmission data. We sort of looked at the approach that PyPSA-Earth used. We weren't sort of satisfied with the data that they were using, and so we were sort of looking for alternative data or different ways to improve our transmission model. So we learned a lot through creating this project. I personally learned how to build a model using open source data. I refined my knowledge of the generation stack, and I really believe that PyPSA can be used to sort of help expose undergraduate students to electricity markets and modeling. Coming into this, I have no background in electrical engineering. I had some tangential experience, but PyPSA served as an excellent tool for me to learn about energy modeling and also refine a lot of my skills with regard to using open data and approaching like larger, harder problems within the modeling space. That's it. Any questions?
Thank you very much, Malcolm, for the presentation. And it's good to hear also that you found PyPSA easy to use. I have a question regarding, you mentioned the transmission grid and that you also evaluated the PyPSA-Earth implementation. So what in the end did you do to improve the transmission grid in your model run?
Yeah, so we haven't sort of done any actual improvements against sort of the 8-bus system with the lossless links. We sort of looked at I think it was, I'm not sure the exact data set that PyPSA-Earth uses, but it was like the OpenStreetMap data, and we were just relatively unsatisfied with how granular that was and how well we could map that data back to the EIA data that we were using. So we just decided not to move forward with that. I think that there is potential to go back and reanalyze some of the OpenStreetMap data and try to map that into the EIA data and actually, you combine those two data sets, but at the current time we haven't done significant analysis of that. We're also very time constrained with creation of this, so we didn't have a lot of time to pursue all options.
Right, thanks a lot. I see a hand from Tom.
Yeah, I was just going to probably go in the same direction, asking about the check against the OpenStreetMap data. And there's also this breakthrough energy model that's been reworked into PyPSA USA by a team at Stanford. It might be worth looking in for the grid data. It would be kind of good to see a comparison between the OSM data and that model, maybe, and some of the more specialized models at some point. We've recently been testing the European OpenStreetMap data against some of the TSO data, transmission system operator data from Europe, and the OSM data is actually pretty good in the meantime, at least in Europe. I don't know how it is in the US.
Yeah, in the future, I'm definitely going to be looking more into comparing the OSM data to more proprietary data sets. Because of the institution that I work at, we had a lot of restrictions around signing NDAs and actually even looking at that data, and we weren't even able to look at it, whether or not we wanted to include the data in our model.
All right, thanks, Malcolm. Are there any more questions? We may have time for one more question, if there is any. All right. Thanks, Malcolm, for the presentation.
Yeah. Thank you very much.
And then we'll move on with the third presentation by Tapio Schmidt-Achert. He's from the FFE, the Forschungsstelle für Energiewirtschaft, a research institution seated in Munich, focusing on energy technology and economics-related topics. Tapio, you're a senior research consultant focusing on applied operations research in the energy sector and specifically hydrogen as a topic. We're very interested in your talk on modeling of global levelized cost of hydrogen under the open source modeling environment, PyPSA.
So I wanted to talk how we use PyPSA, exactly as you said, in the context of energy system modeling for hydrogen specifically and on a global scale at FFE. Basically, FFE, as you can see from the picture, the research institute based in Munich. Nowadays, we also have an office in Berlin, so we're getting more, let's say, international from a German perspective or Bavarian perspective. And also our research here. That was also our kind of motivation. We do have our own energy system model called ESA, like the big river here in Munich. But in this case, we wanted to, first of all, get to know to another energy system model. And then for this application, our own, not open source energy system model is just way too specific for Europe. And we wanted to go global. So that's why we chose PyPSA. To try to use it for analysis. Basically wanted to model global levelized cost of hydrogen. How did we do that? We kind of used the, let's say, brute force approach. We used it by modeling off-grid systems on a MERA2 cell level, so around 50,000 cells. That also shows like already all the importing of data would take way too long with our old modeling approach. So we had to create something new, more generic, more fast, more lightweight. And basically, as you can imagine, this output then is some optimized component size and time series. So quick overview on the left bottom. Basically, there's like onshore wind and open space PV that can be built, some electrolyzers and battery storage, a compressor, some hydrogen storage. Quite simple at the end, but all these components are free to be sized optimally. And then the final result can be seen on the right. There's like different LCOH, so levelized cost of hydrogen on a global scale, that come out of this model. I guess there's also some analysis, so I maybe focus more on the specific things we did. Maybe just quickly, technically, what did we do? We basically built a sandwich. PyPSA is in the middle. We have our own geodata model, which is proprietary. So we kind of included all that data. So the time series for the renewables come from our own geodata model. And then also the output goes back into a database that we use for all our modeling, so that we can exchange data inputs and outputs between different models at FFE. So we basically only used it for this modeling the energy system, or the small off-grid energy system. We used PyPSA. Input data and output data is totally in our own FFE environment. Maybe interesting for some of you who have already models from beforehand. So we were quite well able to include it and integrate it into our modeling landscape. Some results maybe that are interesting. We allowed also obviously hybrid systems. As you can see, greenish colors are hybrid systems. So looking at Europe, looking at Northern America, looking even at Australia, this model yielded for the year 2020, which was the basically cost year, optimal configurations using quite a lot of hybrid configurations, but obviously close to the equator, then a lot of PV in the south of Patagonia, a lot of wind focused or systems. Yeah, this was also interesting for us to see really on a global scale, where is which configuration actually optimal. At the moment, we're looking at this with different cost assumptions for the future. There's some shifts to be seen, but yeah, this is still research in progress. Maybe interesting also to see this one. We kind of plotted, okay, which configurations actually yield interesting or competitive LCOH. There's a few very interesting wind-based locations, a lot of hybrid-based locations in the middle that I have quite competitive LCOH, and then the solar PV in our modeling didn't really yield yet too impressive LCOH. Has also to do that we assumed a constant hourly demand, which we're also currently looking at what happens if we change that. But in this case, it was a constant hourly demand, so PV has a bit of issues. On the right, you can see a bit of the cost structure, which part of this system actually contributes how much to the average, let's say, LCOH in these different clusters. Yeah, with the electricity supply being around 50%. What we specifically looked at in the paper that is also already published as preprint and soon open source published, we looked at the effect of country risk premiums. This means that different countries have a different investor risk. And then there's this effect happening. Dark is always good, dark is cheap. That countries like Argentina suddenly suffer a lot as they have quite a high investing risk. Whereas Chile that is relatively stable for investors with a similar renewable potential stays very competitive, whereas Argentina actually loses a lot of its economic potential. Looking at this on a global scale, the dark countries here being in Southern Africa, Argentina, are countries highly affected by this effect, where the country risk premium is quite high, and thereby the levelized cost of hydrogen are increased by a substantial amount. Our next steps, maybe to show you a bit what we're planning to do. Okay, the paper is actually through the review now, so it should be published soon, open source. What we're looking at model-wise is integrate some demand-side flexibility for hydrogen. We already have our first results on that, and looking at how these effects that I showed here are looking in future years. And with the publication, we actually also want to show how we modeled this, or publish it open source, and hopefully also be able to publish the actual data and the actual results on our open data platform that FFE has. And if you're interested, at the preprint of this research that I presented here is already available. So there you can find more details. Yeah, I hope I stayed in time, and maybe even a few minutes less, so we can keep up with the pace. And if there's questions, we have more time for questions, hopefully. Thank you very much for your attention.
Thanks a lot, Tapio, for sharing. And we indeed have quite a few questions in the chat. I think 2 of them are quite similar. Michael Neswell, do you want to elaborate on your question?
Yeah, well, I have a question. How much battery is used? Because in the model, it didn't show battery costs really significantly.
Yeah, that is exactly the case. As we used 2020 cost data, battery didn't really show to be competitive in our case. We tried it to really reduce it by 50% compared to all other CapEx. Then we saw some batteries being used, especially close to the equator, combined with PV. And then also going to the future years that we're currently investigating, we do see more battery. Yeah.
So you're operating intermittently, and this PEM electrolyzer is able to do it, because I'm hearing new news that alkaline electrolyzers cannot go below 50% power because of hydrogen and oxygen recombination and fire risk.
Yeah,
but is PEM able to follow this intermittent power?
Yeah, that was obviously the assumption here. We really had to keep it very lightweight. Like we had 50,000 cells to solve, so it was 30 seconds around per cell the solving time. So we kept the assumption that it's a PEM and it can go part load, it can go very low. But obviously what you can do always is go modular, depending on the size of your system, then maybe build 10 in parallel or something. And then
exactly.
You can also go lower quite easily.
Okay.
Right, then we have another question from Philip van den Boer. Can you elaborate on your question?
Yeah, how is local actually consumption taken into account?
Yeah, that is our plan. Like this was obviously very greenfield as we did it, and we kind of want to go more brownfield. So we're looking a bit into PyPSA-Earth, if there would be something we could use for this. We'd also be very interested in using local, ideally hourly electricity prices, ideally on a global scale. So if anyone has done anything in this area or has ideas on how to proceed there, that is kind of our pipeline and interest in making this model a bit more brownfield. Yeah, and I have also some local power system effects more included.
Thanks. Thank you. Then we have one final question from Julius Meyer.
Hey, I was just wondering, why did you choose MERA 2 and not ERA 5 for the weather data?
Good question. My colleague Miguel, he's unfortunately on vacation today and he's traveling somewhere. He's our geodata guy. Like we had this data from a previous project. And to be honest, I asked myself the same question and I don't remember. I know there's an answer to it, but I unfortunately don't remember it. Yeah, but basically it was, we had it available, but if you're interested, I can hopefully give you the answer afterwards, what the specific
Okay, thanks.
Yeah.
Good. Yeah.
Right. Thank you very much, Tapio. If there are any more questions, feel free to either directly connect or also keep the questions for the breakout rooms later. There are also quite a few interesting notes in the chat. Here you're also invited to read it along in the presentation. Then we would move on with the fourth presentation of today by Andrew Lyden from the University of Edinburgh. He's a lecturer in energy system economics and management at the University of Edinburgh within the Institute of Energy System. And his research focuses on advancing open source energy system science and working on research and consultancy projects related to net zero electricity markets and multi-energy markets, decarbonized district heating and cooling, and energy storages. Yeah, Andrew, the floor is yours.
Thank you very much for the introduction. So thanks for having me today. I'm going to be talking about PyPSA-GB. So PyPSA-GB is an open source future Great Britain model. And I'm going to focus a bit on two kind of applications of PyPSA-GB today. I'm going to talk about the security of supply in Scotland, and I'm going to talk about locational pricing and the impact that might have on the rollout of heat pumps. So PyPSA-GB really exists in order to try and model the national grid's future energy scenarios. So every year, national grids release these future energy scenarios, which basically map out in different ways how we might get to a net zero energy system. So it counts for not just electricity, but other sectors too. How we might get to a net zero by 2050 in the UK. So there are a few open source energy models that already exist for GB. So probably the most similar to PyPSA-GB is EMBER-PyPSA, or I think it's been called PyPSA-UK before as well. So this kind of seemed to be in development at the same time as I was developing PyPSA-GB. So just as a comparison, it does have some future data, but it seems a bit more limited in that it only looks at 1 year, 2030, and a few of the scenarios. Other couple of models for the UK have been HiRes and UK Calliope. And so they're focused on kind of planning and doing these kind of capacity expansion things out into the future. So they don't have like ready to model future data within the model. And that was kind of the aim of PyPSA-GB, was to have this future data from national grid's future energy scenarios that a lot of people in industry and academia and in the UK know and kind of have a lot of trust in, I guess. So the idea was to have PyPSA-GB as a kind of data set for basically generating PyPSA models that have the national grid data underlying it. So an example of this, one of these data sets, I'm not going to go through all of the data sets, but one is around marginal prices. So this graph here shows marginal prices of things like coal, gas, and oil. So on the left, you can see the historical data is there. So we can also model historical years, which is good. But then we could also expand out into the future based on what the future energy scenarios have kind of estimated what future marginal prices might look like. So I'm going to go into kind of examples of what research is going on at the moment, what's happened in the past, what's going on at the moment, maybe what's going to happen in the future too, using PyPSA-GB. So this graph here shows a study that was looking at carbon intensities at system level. So basically we're looking at if we add in more marine power at certain buses or locations around GB, what would be the impact on carbon intensities at the system level. We're also use PyPSA-GB for other studies around things like storage, so ultra high temperature storage, seasonal thermal energy storage, which is one of the main reasons that PyPSA-GB started, was to look at seasonal thermal energy storage and that kind of system integration of these technologies. There's also been work around future hydrogen demand supply network, basically generating a PyPSA model of hydrogen, what it might look like in the future for GB. But today I'm going to focus in on electricity system security supply in Scotland, and then I'll talk a bit about the impact of locational pricing on the rollout of heat pumps in the UK. So the first example was a bit of work that we did for the Scottish Government on through the climate exchange programme. And they were interested in basically what does the future look like in Scotland in terms of security of supply for the electricity system. And so we used PyPSA-GB as a kind of data set to firstly kind of explore what are the kind of anticipated issues. So this graph here shows the dispatch of generation and storage zoomed in Scotland as operating as part of a wider GB system. And you can see here that what's actually happening is that Scotland is providing a lot of exports, so basically providing security of supply to the rest of GB through this B6 export. So this large negative sum here is actually exporting, and this black line is showing the peak GB demand. So during peak GB demand, we're having a large export of electricity from Scotland. And that's kind of what we expect, because we're going to build lots and lots of new renewables, mainly wind, in Scotland. So we're going to see a massive increase in generation capacity, basically. So to kind of look a bit further into this, we did some stress testings. We've generated these different stress tests around the Scotland. So looking at things like, well, what if there's a long period of low renewables, or an extreme example where we actually looked as if there was no connection available at all to the rest of GB. And basically we use PyPSA-GB as a data set to feed into some loss of load expectation calculations. So our models show kind of that even under these stress tests, the security of supply is still likely to increase. So it's, even when we account for these quite extreme sometimes, security of supply will likely increase. So the dotted line in blue is the LOLE for 2021 in Scotland. And you can see it's only really in 2025 or 2030 under a failure of B6. So this is the connection between Scotland and the rest of GB, between England and Wales. And that's the only time where we see an increase in LOLE from historical values. All the other stress tests, we actually still see this decrease because we're building out so much renewables in Scotland. The second kind of example that we looked at was looking at locational pricing and how that might impact on kind of end electricity consumer costs, and therefore how basically the operating costs of heat pumps. So in the UK, there's a big contentious debate at the moment around electricity market reform. Zonal nodal pricing have been talked about. Recently, the government ruled out nodal pricing, but zonal pricing is still on the table, but it's a very contentious and kind of hot topic. But while we're thinking of reforming markets, we're also thinking about this massive increase in the rollout of heat pumps for decarbonising domestic heat. So I've used PyPSA-GB to basically do some analysis around this. So this is how we did some analysis for looking at individual heat pumps. So we can use PyPSA-GB to simulate kind of wholesale prices of the system, and then combining this with models for heat pumps and individual house, and we can actually calculate a kind of look at what heat pump operating costs might be under zonal pricing and also into the future as well. We can also look at this at the kind of system level too. So National Grid also have their own projections within the future energy scenarios on what they think annual heat demand might look like, what the number of heat pump installations across different regions might be in the future. So we use this to basically come up with a kind of regional heat pump demand profile in early time steps, which we can then apply into PyPSA-GB for the different zones across the system, in order to figure out what the system-wide operating costs might be in the different regions. So since looking at that kind of locational pricing things, we've also done a bit more work in terms of being a bit more interested in also including things like constraint costs and balancing costs. This is some latest work that we're doing that's been led by Lucas Franken, who's a PhD student at Edinburgh. So he's looking to try and use live grid data to model what national or what nodal or zonal pricing would actually be at the current time. So hopefully there'll be some nice outputs on that soon. And I think there's probably an interesting kind of research we could do with incorporating kind of the future PyPSA-GB data. So to kind of conclude, there's lots of kind of future research and development we would like to do. So there's software things, and we want to kind of take some more inspiration from the PyPSA-Eur, PyPSA-Earth kind of workflows that make good use of SnakeMake. As our models got more complicated, I think having an improved workflow would be really beneficial. We are doing already sector coupling is kind of happening as we develop domestic heat models, hydrogen models. We want to incorporate that into the main PyPSA-GB, which is currently focused on electricity. I'm very interested in modeling electricity markets, so I'm interested to see and be connected with people who are also interested in that kind of area. And I think just more generally, kind of there are big lessons for GB. I think this debate that's going on around electricity markets is very contentious, and it would be really useful to have a lot more transparent models that aren't just hidden behind consultancies, but can be open and trusted by others. And more open source models in the GB would be great. For example, if National Grid actually just opened up all their models and data sets, there probably would be no need actually for PyPSA-GB. but PyPSA-G does exist, so we've shown that it's been used and applicable to a wide range of research, and I think there's a lot more we can do in the future. Thank you for listening. Happy for any questions.
Thank you very much, Andrew. We have 2 questions in the chat. The first one by Kumari Sandia. Can you elaborate on your question?
Hello?
Yes, we can hear you.
Okay. So which kind of thermal energy storages have you used for curtailing energy from the wind energy?
Okay, so thanks for the question. Yeah, so that study was looking at seasonal thermal energy storage. So it was really focused on kind of underground thermal storage, such as pit, we're not with the pit yet, but looking at borehole thermal energy storage and aquifer thermal energy storage. And I think the stuff that we've published so far has been on borehole thermal energy storage, where really the big challenge is trying to be able to, because borehole thermal energy storages are quite limited in how quickly they can charge and discharge. So one of the big challenges is how we can, one, accurately capture that in models, but also how quickly they can react to curtailed wind, which can often be a very quick response that you need to actually capture that curtailed wind or otherwise curtailed wind.
Okay, thank you.
Thank you. Maybe one more question, short one from Tom.
Thanks, Andrew. It's very interesting to see the drop in Lola from 2030 onwards. Could you give us a bit of intuition there? What's happening when there isn't too much wind? Is there some more firm generation of storage there that's catching, that's helping the system get through these events?
So the system, the kind of projections also do account for a slight increase in kind of conventional like thermal, like dispatchable power generation from something like they assume that it's going to be a hydrogen power plant in the northeast of Scotland, but we'll see if that actually happens. But there's also increases in things like pumped hydro, so there's almost a doubling of the amount of pumped hydro that's there. Big increases in battery storage, but most of it is driven by the huge increases in renewables that are going to be seen in Scotland. There's a slight increase in peak demand that is projected, but the amount of wind that's going to be built in Scotland is incredible. So.
But if they have an event that goes on for multiple days, for example, so the pump storage and the batteries are all empty, and I guess the hydrogen storage is the one that's on the line, did they take account of the sort of temporality to the failures as well?
Yeah, we tried to account for that temporal part as well, and so one of the stress tests was low renewables, but it wasn't zero renewables. It was like basically down to 10%. So that still covered a fair amount of the peak demand, and then it was all these other things that were coming in to do it. So I guess the LV probably doesn't account for over those days. Maybe it's still just looking at the peak demand moment. Yeah.
Thank you.
Right. Once again, thank you also from our side, Andrew. We'll then move on with the 5th presentation of today by Agnès François. She's with FEMTO-ST Institute, which stands for Franche-Comté Electronics, Mechanics, Thermal Science and Optics, Science and Technologies. It's a research institution with a strong energy department based in France. And you are, amongst others, working on the Haast project, studying the roles and impacts of hydrogen on the transition towards energy independence. The floor is yours, Agnès.
Yes, thank you. Can you hear me?
Yes.
Okay, great. So thank you for the introduction and good afternoon, everybody. My name is Agnès François. I am a last year PhD student from France, and I'm working on the integration of hydrogen in non-interconnected islands. I always have to, okay. So the objective of my thesis is to assess the impact of hydrogen on insular grids. And to do so, I'm using PyPSA to model the grid and simulate and optimize the whole energy system of non-interconnected islands. So after a short introduction, I will present you my work with PyPSA. Starting with grid modeling, and then I will detail how we study electricity self-sufficiency and energy self-sufficiency aims of islands. And I will finish with some additional options we added to PyPSA and some perspectives we have for the coming weeks and months. So as the introduction said it, my work is part of the EEL project. The EEL project works on the integration of hydrogen into weakly or non-interconnected networks. Among this project, we study three territories, three French territories: Corsica, Reunion Island, and French Polynesia. It's three very different territories with three very different energy contexts, and we study all of them at the same time with a generic use of PyPSA. I am working more specifically on Reunion Island. It's a small island where I'm currently living. It has no interconnection at all, and there is 850,000 inhabitants in 2,500 square kilometers. I put some graph at the bottom to show you how dependent the island is on fossil imports. And it's a real issue locally because we have a French law setting energy autonomy for 2030, namely in 6 years. That's why we are studying the grid of this island specifically. So to study the grids, we are using PyPSA to model it. We are modeling the high voltage network of the island with its 25 substations and its 520 kilometers of 63 kilovolt lines. Every substation is modeled as follows. So every substation is modeled by an electricity bus. We also have one or more generators defined by the installed capacity and the carrier. So for the island, we have solar, wind, water, biomass. We also have electricity consumption, so a load, and if existing, a battery. So in order to study the electricity autonomy aim of the islands, we allowed lines capacity to be extendable, and new storages were also added to every substations, once again with an extendable capacity. So this is to assess the electricity self-sufficiency in the medium term of the island. So we tested several installed power generation capacity scenarios. You have one on the screen, and we obtained several results. We obtained investments in line reinforcements and also investments in new storages. As a result, we also have the hourly electricity mix as given by PyPSA. So this was for the electricity self-sufficiency aim. Then we studied the integration of hydrogen for mobility in order to study energy self-sufficiency on the island. So to integrate hydrogen, we added to some substations 2 new buses, a low pressure hydrogen bus and a high pressure hydrogen bus. We also added an electrolyzer link, a compressor link, a hydrogen storage, and hydrogen consumption. So there on this modeling, every link and every storage is extendable. So this allows us to assess the energy self-sufficiency aim in the long term. So once again, we have our investments as a result. Here on the left, you can see investments on new electrolyzers and investments in new storages, batteries, and hydrogen storages. And we still have the hourly electricity mix as a result of our system. To obtain all of that, we added some constraints on PyPSA. First, as we are modeling local renewable production, we had to add a constraint about limiting annual production of some sectors. For example, the biomass sectors and the hydropower sectors were limited with an annual data. We also added some capacity factors to hydrogen technologies to force electrolyzers and compressors to work at least a certain amount of time during the year. We also added a constraint to limit total installed storage capacity because locally batteries are a real issue. They have to be exported at the end of their life. So we have to limit the use of battery on the island. And finally, we added some attributes to some components. So we added fixed and variable environmental impact and water consumption to the following components: generator, link, storage units, and lines. This was done in order to constrain and limit water consumption, which is once again a very important issue on an island. And this was also made to perform a multi-objective optimization implemented with the epsilon constraint method. In the multi-objective optimization, our second objective is the minimization of environmental impact. I will conclude. I have no idea how much time I have left. The next step of our work will be the integration of hydrogen as a means of storing electricity over the long term. In particular, we will integrate fuel cells into our system, so fuel cell link. Then we want to publish our code in order to offer to people interested a way of modeling insular grids. So to do so, we are aiming for just publication, and we also have documentation and a GitHub repository on the way. And finally, not me, but a colleague also worked on an interface of which you have some screenshots on the screen. It was done in order to have an easier configuration and visualization. Thank you for your attention, and I will answer if you have any questions.
Thank you very much, Agnès, and you are very well on time, so no worries. There's still plenty of time left for questions. And it was very interesting to see that this is one of the rare cases probably where you can model then the location at full resolution. That's how I understood it.
Yes.
At least.
Yeah, we can model the whole grid very easily. So this is very interesting to use PyPSA for that.
Yeah, very cool. And here I have a question regarding the transmission expansion. Could you give a range and how, in percentage maybe, how much the grid needed to be expanded in your model runs?
Yes. Once again, someone said it in the previous presentations. It's the actual capacity of lines is a data difficult to obtain here. So we had to make some assumptions according to other studies. So we have around 40 MVA capacity for most of the lines today, and with our simulations, we would reach around 50, 60 MVA in the future.
Right. Thank you. Are there any more questions? I see a hand from Tom.
Yeah, thanks. So it was very interesting to see the hydrogen demand because it's mostly for transport, right? I got the sense there was enough biomass and bagasse there that you probably wouldn't even need the long duration energy storage. Is that what your feeling is as well?
Can you repeat the end, please?
I was wondering if there's so much backup from the biomass side of things with the bagasse, you maybe don't even need to store the electricity as hydrogen in that system.
Yes, actually, so this is one of the points I studied a few weeks ago. Local production won't be enough to provide energy for coaches and planes and boats. It won't be possible because, yeah, there is not enough local resource. This is one of the results of my thesis. So some imports will be needed either way if people want to keep taking planes or boats or use their coaches.
But probably a lot of the transport could be electrified. I mean, a lot of the boats and the buses and so on could be electrified, which would be more efficient and then make more energy available for the other sources, other demands maybe.
Yes, we modeled individual vehicles to be electric, and hydrogen is used for producing e-ammoniac and e-kerosene. It's not used as such in planes and boats. And for coaches, we studied different case studies where hydrogen is more relevant than electricity because of the local relief and local temperature also.
Does the e-kerosene, are you taking the CO2 from the biomass then, or is it coming from a different source?
Can you repeat? I didn't get what you said.
For the e-kerosene, you need a source of carbon.
Yes.
Is that coming from the biomass then in your case?
This is also a limitation because if we consider the local consumption of the sector, today a lot of CO2 would be required, and even with local biomass, we don't have enough CO2 to produce e-kerosene. So a lot of limitations about energy self-sufficiency.
Thank you.
All right. Once again, thank you very much, Agnès, for your presentation. And then we'll move on with the final presentation for the first session by Peter Klein from Meridian Economics. Meridian Economics is a specialized consultancy providing strategy advice, analytical capabilities, and decision support. And Peter Klein has, over the past 12 years, developed expertise in both thermal and renewable energy systems with a strong focus on modeling both the system level and specific processes. Peter Klein, the floor is yours.
Great, thank you. Can I just confirm you can hear me okay? Been struggling with my network a bit.
Yes, loud and clear.
Okay, great. So thank you for the opportunity. We're going to present some work that we did recently related to a national integrated resource plan that was released by our Department of Mineral Resources and Energy for public comment. And just some of the work we did using a version of our model that we've been developing called PyPSA-RSA, and how we use that to sort of enable stakeholders to have a bit more data to make informed technical submissions to that process. Just a very brief introduction to Meridian. We're a small consultancy. We work across the sort of energy and climate economic space. And I think some of our real key work was around we developed a concept around the just transition transaction, which sort of fed into a lot of the work that was done at COP around the JET IP and some of those funding arrangements that came into being with South Africa and overseas partners. In terms of just a brief snapshot of what the energy system in South Africa looks like, we're still heavily dominated by fossil fuels. We have in the order of 40 gigawatts of coal capacity, and we've been steadily ramping up new generation, mostly from renewable energy resources. We have quite an extensive land area available for projects, and we're one of the few countries, I think, that has a combined excellent wind and solar resource. So we have essentially in the order of, I think it's 11 renewable energy development zones that you see highlighted in these images. And they really cover some of these high resource areas, and they streamline for renewable energy projects to happen. Capacity factors on wind plants easily over 40% in some of those areas, and in our Northern Cape we can get upwards of 30 to 35% on single axis tracking plants. So excellent resource, but we do have a challenging network topology. So historically all of the generation was located to the northeast of the country, so you can see all the coal plants there, with our major load centers in what we would call our provinces, Gauteng and KwaZulu-Natal, which are again you can see where the network, the 400 kV network there is quite extensive. And then we have very long transmission lines to other load centers. So we have down in the Western Cape and the southwest of the province, and almost very little load in the Northern Cape and Eastern Cape, where a lot of these excellent solar resources are. So part of the challenge is really that now we need to embark on a significant grid expansion in order to now reverse that direction and put a lot more generation in these high resource areas, but we have to move all of that power to the major load centers, which are quite far away. So our national utility ESCOM is embarking on a significant expansion to both its 400 kV and 765 kV networks. South Africa has also been struggling with generation capacity shortages, and this has led to new build programs on massive coal-fired generators, and those power plants have gone significantly over budget on construction, and you can see that that's led to significant increases in energy prices in real terms. But our most significant challenge has been load shedding, and we've had sustained capacity shortages for over 10 years, actually, but reaching a peak of about 6 or 7% of demand was shed in 2023. In terms of generation happening in the country, a lot of the renewable generation was all driven by central procurements and bilateral PPAs, but those central procurement programs stalled around the late between sort of 2016 and 2020. And what we've seen in the meantime is relaxation of some regulations around new generation. Before there were caps that you had to get a license in order to get new generation, and now those caps have been lifted, and you can see the significant response that there's been from our private sector, which is now mostly distributed PV projects amongst commercial, industrial and residential customers. In terms of projects moving forward, there's our presidency is tracking a lot of those projects, and there's in the order of 20 gigawatts of new private sector projects being developed. South Africa is quite an interesting case study because we are due to decommission our extensive coal-fired fleet over the next sort of 2 decades. And we have a lot of interesting transition debates that are happening within the country about what kind of capacity needs to replace this massive coal fleet. So the South African government recently released a draft integrated resource plan for public comment, and really it was met with quite a lot of criticism because the plan was seen as being very opaque. The input assumptions were initially not very clear. The modeling approach was not clear, and some of the input data sources that were used were quite out of date. So that the sort of what I think stakeholders were looking for as part of this commenting process is to have some techno-economic analysis that can underpin some of their comments that were submitted to the department. So that's what we spent about a month and a half working on. So we didn't have a lot of time to do this work. But I think the first useful contribution, and this is freely available on our website if anyone wants it, we did an extensive comparative analysis of costs. So we took a range of pretty much most reputable data sources that we could find, from AEMO in Australia to NREL, EPRI, IEA, some of our own work and local cost projections, and we really mapped out each of those techno-economic parameters for a whole range of generators. And what you can see here as an example for wind, the dashed line here are prices that were achieved in our public auctions, and this red line that you see right up here at the top was the input assumption into the IRP modeling. So immediately pointing out some challenges around input data, lack of learning rates, and really being substantially higher than prices that have not only already been achieved in our market, but with what most other data sources are saying as well. So this is available as an Excel workbook and lots of tabs, and we've done our best to try to document that as closely as possible. So anyone's welcome to use it. Please give us some comments if you find any bugs. What we did then was feed this updated input data into our PyPSA model, and really with the aim of it being as transparent as possible. So We've made the model fully available, all the input data, and we're even holding a series of workshops now where we're taking stakeholders through the model, the data, making all of that publicly available for everyone to use. And it really contrasts with the approach, I think, of some of the commercial tools and really them being a bit more black box in nature and difficult to interrogate. Just in terms of a very quick snapshot of the PyPSA RSA architecture, it was adapted from an initial PyPSA-ZA model that was done by Jonas Hirsch and Joanne Kallitz. And really what we landed up doing was building functionality into that model that could make it comparable with the Plexus type studies that were done for South Africa. So we have a lot of focus on transition modeling, perfect foresight, running a wide range of scenarios spanning the uncertainty. And we found that it helped to overlay a bit more of a user-friendly scenario configuration in terms of different Excel files that made it easier for people in the business that, in our business at least, that don't use PyPSA to be able to engage with the data in tools that they are more familiar with. In terms of some weather resource modeling that we did, we do use Atlight as kind of a fundamental tool, but we did do a fair amount of tweaks to it, and we did add additional data, also looking at from PySAM and the NREL National Solar Radiation Database. And then we also, in terms of wind modeling, we have the Wind Atlas of South Africa, which includes some more mesoscale modeling, so a bit higher resolution than what's available in ERA 5. And what you see on the right-hand side is we took all the utility data from the utility scale PV and wind plants in the country. We rebuilt each of those plants in the model, and we could compare the combined fleet output. And you see there's a very good correlation across both wind and solar. So just finally, in terms of some of the results that came out of the study, I know this is a lot of information on one slide, but we tried to develop a sort of slide dashboard for each scenario where we could capture all the information in one slide, and then you could easily compare scenarios against each other by flipping through them in a slide deck. So what you see on the left-hand side is essentially the cumulative new capacity from 2025 to 2050. The orange bars are essentially what came out of our model, and the solid black line is the reference case from what was modeled by our Department of Mineral Resources and Energy. So you can see that we have a significantly higher levels of solar PV and wind, and better and much lower use of gas-fired generation. As part of our modeling, we did do a specific split of combined cycle plants. So we optimized the OCGT portion separately to the auxiliary steam boiler. And we did some modeling around that. But ultimately, you can see the net effect of this is that our model predicts a significant reduction in the requirement for gas. So on the left-hand side, you have what was in the IRP from the government, and the right-hand side is our recreated scenario. And of course, the moment we add in a growing price on carbon, we can see how that really significantly changes the outcome and reduces the dependence on gas, while by 2050 getting to about 1,800 Rand a ton, or about, what's that, 90 euros a ton, getting close to a net zero by 2050 commitment. So I think I'm probably slightly over time, so I'll pause for there. But a lot of this detail and modeling is available on our website. And we're happy to engage if anyone has any questions or doing something similar and want to compare notes. Thanks.
Thank you very much, Peter, for the very elaborate work that you have done. We may have time for 1 to maximum 2 questions before the break. I see a hand from Tom.
Peter, this is so impressive. I think it's one of the most impressive studies that's being done with PyPSA for any single country. So it's really nice to see it. I mean, one thing you could emphasize to them, as well as the fact that the costs might be lower, is that the price volatility might be lower, because depending on that much gas in a volatile world market, if you translate that into electricity price spread, it's going to be very high potentially. And that might be one other way to influence the discussion. Thanks.
So very interestingly, we had a technology agnostic public procurement, which was the requirements made it very suited to a gas-fired generator, but any technology mix could apply. And the projects that applied were at the lowest recorded gas price in recent history, and they just got in as winning bids. By the time those projects didn't eventually close, the only projects that actually closed were solar PV and battery, which were only marginally more expensive than the cheap gas at the time. But once obviously with the gas crisis and everything, prices were significantly more expensive. So much more downside risk.
All right. Thank you, Peter. I think then we would slowly close the first session, and we would, of course, once again, kindly invite you to stick until the very end. There are many more exciting presentations coming from all around the world. We are quite good on time. I think we would keep the break just a tiny bit shorter, so we'll still start at 4:40 in 8.5 minutes. If that's fine with you, you can stay in the call. Yeah, looking forward to the presentations in the second half.
So welcome back, everybody. I hope everyone had a pleasant short break and is ready for round 2 for our lightning talks. As a next speaker, we're going to have Marta Frysztacki from Open Energy Transition. She has been a core developer of PyPSA and its associated models in the past years, and today she's here to represent OET, Open Energy Transition, a young nonprofit think tank and software company that she co-founded. One of their main tasks is to provide support to PyPSA users all over the world and PyPSA using companies. And these companies usually use customized versions of the general PyPSA models, such as PyPSA-Eur and PyPSA-Earth. So in her talk, she will hopefully share some secrets with us on how to best synchronize these customized models with the upstream open source developments. So yeah, hopefully something of value for everybody here. Floor is yours, Marta.
Hi, thanks for the introduction. Yeah, very nice to present today. Let me just share my screen. I hope you can see it now. Yeah, very great to be presenting here, and very nice to see all the various developments before, and also nice to see the group again. Haven't been in touch in a while. So yeah, today I will present our role in supporting PyPSA workflows and developments. So first of all, we have seen that the PyPSA universe offers a lot of solutions to so many problems in the energy modeling and planning landscape, ranging from energy data, where we have a lot of very nice packages for different applications. I won't present them now. I guess most of the people here are familiar with them, but they range from renewable time series across our database of generation or generation plants, transmission networks, distribution networks, and also technology assumptions. And then we have the models where PyPSA is just at the core, but we have all of those integrated tools, PyPSA-Euro, PyPSA-US, PyPSA-Earth, and PyPSA. We have heard so many names today. And those are just a subset of the models. And also we have solvers and interfaces, which is something I don't want to focus on today. And at the same time, the universe can be also very technical and might be relatively hard to use if there's no support available, particularly seeing all the new Git commits in the main repository, upstream repository, with all those new coming releases, new features being implemented. But at the same time, you want to customize your own model by integrating your own data, which might be private, which might be public. You might want to update technical parameters of different technologies or assumptions, or might need help to visualize the input data, but also the results. On the energy system model side, you might want to refine your own constraints or implement new technologies. So basically, you want to adapt the model or develop your own one, which you might want to share parts of it, and some parts keep to yourself private due to data restrictions or the possibility to be allowed to share the data. So how can I manage workflows, etc. So our role here in supporting workflows is manifold. I want to focus here on 3 main pillars. So we provide workflow support, for instance, for different PyPSA workflows, which continuously benefit from the community and upstream improvements. We also help develop new features and models, so to understand and assess the impact, for instance, of a new technology you might need help to implement into one of the PyPSA versions, and might need also help to develop scenarios to analyze the economical impact. Or we also do tailored modeling and scenarios where we help to scrutinize model assumptions, explain in very high detail what the model is doing, how the different sectors, for instance, interact, how do the different technologies interact, which helps to accelerate the discussions because of this very technical dimension of the model, and it might be still relatively hard to understand what is exactly going on. In this presentation, I want to mainly focus on the workflow support and on the tailored model and the scenarios. So with the keeping updated and workflow support, what we mean is we want to create a nice energy system model which is based on PyPSA Europe or PyPSA-Earth, and which is continuously maintained, ideally by the community, not by yourself. So you have the central repository, and in the beginning you have nothing on your computer yet. After a few iterations, you might realize, okay, the first thing I want to do is create my own fork, which is either hosted on GitHub, but it can be also hosted on your server, where you can do high computational computing, and then you clone your fork on your local computer. On your local computer, then you can work and adapt the model, include new data, include new features, new constraints, whatever you want, and push that to your fork on your server. However, after a while, it might be months, it might be weeks, it might be even a year, you realize, oh wow, there has been so many great features upstream. So PyPSA Europe has changed so much. There are so many new features. I want to really benefit from all of these features. So let's merge it now. So I want to update my fork. But I have all those many merge conflicts. So that's usually a problem, especially if you haven't updated your repository every once in a while. And because of that, we have developed an automated workflow to keep this private repository or your fork on your server continuously updated, so that you basically can get a pull request automatically whenever something has changed in the upstream repository, so that you are continuously updated and you don't have to resolve all those many merge conflicts in the same time, but you can really take care of each merge conflict. There will be still merge conflicts, but maybe not many in the same time, one by one. So with that, you have basically achieved your goal. You have a very nice energy system model that is continuously improved by the community, and it's automatically maintained with all the new incoming features. The benefit from that is that you're much faster, so you don't have to manually, well, first of all, clone or copy paste code, or you don't have to resolve all those many merge conflicts at the same time. You get all the expert knowledge from the upstream, and if you in the end want to contribute something back, you even get an extra straw for collaboration. We have, I think, one of our great collaborators here is also in the call with Frysztacki, who will hopefully benefit from this very soon. And then the second bit that I mentioned, that we also provide help with customizing a study. So what sometimes can happen is that you have seen a study published in a very nice peer-reviewed journal with a potentially high relevance, but it is very technical and therefore it is hard to reformulate and adapt. But there are still some missing things in the study that might be very relevant to really understand the full picture. And for that, there is a need for stakeholder engagement and also modelers. So there is a very huge, many people coming to the table. and there's a need to adapt the study to specific needs. So for instance, you want to include missing technologies or change some modeling assumptions. And the output of that is a study that we have based on an open and peer-reviewed, very nice methodology and verified assumptions for policy advocacy. So we have the transparent model and a reproducible workflow in the end. Yeah, so the big problem here is that we have a very large sector-coupled model, which is not entirely clear what is going on where to make changes or include features. And the scenarios are mostly research, but not policy focused. And what is actually needed in the stakeholder engagement or for policy that is comparing those results against business as usual or against a system of today, include missing technologies. So in this case, it was nuclear, coal, and lignite, and include also relevant methodology that was developed in the same time, but was never combined in one study only. And for that, we need a lot of regular communication with the stakeholders, with the modelers, to get the right assumptions and the right methods in the right place. And also in the right time. And then in the end, we can publish openly a reproducible workflow, which is based on PyPSA Europe or PyPSA-Earth, but it's not a new model. So it really just adds a couple of new features, either directly into the model or provides an additional on-top workflow, but doesn't create a wholly new model so that we can benefit from the upstream developments. Yeah, these are the people we are currently working with for the study. So the goal here was to analyze and understand the impact of building insulation on the entire EU system. The background here was first that the study was using endogenous modeling to optimize investments in building retrofitting from people who are here also in the call, I think, most of them. But it was an overnight optimization and missing business as usual, so as a benchmark, so to understand what is the benefit against just continuing what we're doing today. This is a result from the study. I cannot really, I guess I'm already close to my time limit, so I will just present the business as usual scenario where we have added existing power plants, for instance, nuclear and fossil fuels to the system, which wasn't there in the first study. And this is included in the sector-coupled PyPSA Europe version and compared against a 2022 historic result. And we can see here a very good overlap. In the interest of time, I will skip here now to the end. Sorry for that, but thanks for the attention.
Thank you very much, Marta. Was really interesting and also quite entertaining. I have the impression that a lot of people know that feeling of having about 1,000 merge conflicts and having to resolve them. Let's have a look at the chat if there are any questions. I've seen one question of Carla, which was already answered by the active Max. Are there any more questions? You're also free to raise your hand.
There's a question about concentrated solar power, I think, from Carla Guerra.
Yes, hello.
Yes, we can hear you.
Yes, my question is, for example, how could concentrated solar power be included in PyPSA?
Max already replied to that also in the chat. So it's already added in PyPSA-Earth, but currently not available in PyPSA Europe, which we are currently working on to integrating it there as well.
Okay, thank you.
Great. I think, then there's another question from Tom.
Just to understand a bit with the whole merging, how do you still have to deal with merge conflicts, I presume, when you make a change that conflicts with the upstream change, or is there some special way of avoiding that? I mean, you don't avoid the problems of merge conflicts, I guess, but it makes it a bit smoother, maybe. Is that right?
Yeah, that's exactly right. So I guess I can just pass the question to Sid, who's also here in the call, who has actually implemented this thing. But from my the way I understand it, it's whenever you get like a pull request in the upstream repository, you also get a pull requests on your own server, and then you can deal with merge requests really one by one instead of having to pull all the changes which you have forgotten about in the past years.
Okay, thank you.
Yes, if I can jump in, yeah, I think the main advantage is you only resolve a conflict once. And so if you have a similar code change later, when you merge the second time, you wouldn't resolve the same conflict again. So Git automatically figures out which parts have changed. And yeah, so and second advantage would be that you have the history of both all the files in the upstream as well as all the files in the fork. And for each of those, you could see line by line who changed it when and so on.
Thanks.
Amazing. Thanks for the clarification, Sid. Then I'd like to welcome our next speaker, Ganesh Doluweera. He is the technical leader at the Canada Energy Regulator. Furthermore, he works as an instructor and researcher at the University of Calgary, where he focuses on modeling and analyzing energy and environmental systems. And at the Canada Energy Regulator, they use PyPSA to build an electricity model for the most recent long-term net zero energy outlook. So in conjunction with other models, this model already provides the base for ongoing policy design. And today, Ganesh is going to present the regulator's model setup and also highlight some of their key findings and discuss the lessons learned. Welcome, Ganesh.
Thank you, Caspar. Can everyone hear me well?
Yes, I do.
Thank you. And I'm assuming you can see my screen as well. We're happy to be here. And I should say good morning, good afternoon, and good evening, depending on where you are. Like Caspar mentions, I'm with the Canada Energy Regulator. As part of our energy information mandate, we produce, periodically long-term energy outlooks, energy projections, exploring how possible energy futures might unfold for Canadians in the long run. And then we've been doing this for several decades. The first publication, long-term energy outlook was in 1967. And these long-term energy projections or outlooks are widely used in Canada, by decision makers and energy analysts. Of that, outlook series or energy projection series, the most recent publication was Canada's Energy Future 2023. I should have mentioned our long-term projection series is called Canada's Energy Future Series. And like I said, the most recent publication was the one we published in 2023. The EF 2023 in particular focused on the challenge of achieving net zero greenhouse gas emissions by 2050 in Canada. Our scenarios, we produce our projections under different scenarios. These scenarios cover all energy commodities and all provinces and territories in Canada, which I will speak a little bit in detail. The objective of my presentation is to, show our model setup, and also, depending on the time, show some results that came out of EF 2023. Like I mentioned, to produce these long-term energy projections, we use a suite of energy system models, like interconnected energy system models. And then also we feed them with several assumptions depending on different scenarios. And then these assumptions include policies, energy prices, technology development, and also some macro dynamics, things like GDP growth, population growth, and so on. Of our energy suite of energy models, the key two of the most principal items are the energy demand model, which projects which determines what is the end use energy services of Canadians, depending on different economic sectors, whether it is residential, commercial, and industrial, and so on. And the other key item is like electricity supply model, which in 2022, we completely overhauled. Like I said, this projection system has been there for a very long time. But in 2022, we actually overhauled the electricity supply model completely and then implemented that using PyPSA. And then these two models, these models interact iteratively to produce our long-term energy outlook. And then the electricity supply model, like I said, based on, that we implemented using PyPSA, obtains information to run from other models, from our input data set, that includes like technology data and so on. And then also we get information passed from the demand model on electricity side. And it passes back other information like energy prices, fuel demands, and emissions, and also investments, like major investments that happens in the electricity sector. Now, Canada is a very big country. There are 10 provinces and 3 territories. Each jurisdiction has their own electric power system. Pretty much operate independently. So in our model, we represent each region or each province or territory by a single node. In the current implementation at least. And then all the provinces got interactions across provinces, as well as there are interconnections with United States. Our model captures all those interconnections, and then we model all that as a PyPSA network with, like I said, 13 nodes and several interconnections. Let me get back to our EF 2022, okay, Energy Canada's Energy Future 2023 report. So the report produce energy projections under 3 scenarios. They differ mainly by the underlying climate action across in Canada as well as in the world. Like I said, the key challenge that we investigated in the last projection was, how would Canada's energy system would look like in a net zero scenario. So we had 2 net zero scenarios. We call global net zero scenario and Canada net zero scenario. So the key difference is in the global net zero scenario, Canada reaches net zero by 2050, along with the rest of the world, and then the whole world has very strong climate action to reach net zero emissions by 2050. In Canada's net zero scenario, we looked at a world where Canada reaches net zero, but the rest of the world, will have moves a little bit slower, so not necessarily reach net zero by 2050. And in current measure scenario, that scenario presents a projection if no additional climate action is taken beyond what is currently in place. So basically, the net zero is not achieved by 2050. So let me get to some some results. So the figure that I show here shows the end use energy mix used by Canadians in the 3 scenarios. The key thing is across the 3 scenarios, we project little change in end use energy services Canadians would receive. In other words, we have the similar level of transportation. Our living space will have the same level of comfort across the 3 scenarios, but the actual the energy system in 2050 under net zero scenarios is very different than what we have currently. We project electricity becomes the dominant end-use energy source, while the fossil fuel, so the electricity is in this yellow wedge, and then fossil fuels are in dark black, dark gray wedge. So fossil fuel consumption reduces significantly, and electricity demand, the electricity becomes the dominant end-use fuel mix. Like in Canadian, fuel mix, like end-use and fuel mix. For example, in the global net zero scenario, we project that electricity will account for about 41% of the total end-use energy consumption by 2050 by Canadians. So the result is we see the electricity demand more than doubling in both net zero scenarios, and then we see electricity consumption growing pretty much in all economic sectors, whether it is transportation and or residential and so on. The key reason being we project a lot of end users, whether it is home heating or transportation, will be electrified in both net zero scenarios. We also see two additional demands emerging. The key one, the one at the top, which is the kind of like a purple wedge, is hydrogen production, because we project some of the energy end users will consume hydrogen as a fuel, and that hydrogen need to be produced. And then some of that hydrogen is produced by electrolysis, and so that also becomes like a new source of electricity demand in Canada. So like I said, the electricity demand more than doubles. That means we have to produce way more electricity than what we produce currently. So the figure on the right shows the incremental the changes in generation mix in 2050 compared to the current levels. We project in both net zero scenarios, Canada's electricity sector transforms to accommodate increasing electricity demand, while also rapidly decarbonizing the electricity supply. We project by 2050, more than 99% of electricity is from non-emission sources with no emissions or low emissions, and fossil fuel consumption in the electricity generation sector, almost completely diminishes. Not only electricity sector becomes the dominant part of end-use energy mix, the electricity sector is also the backbone of Canada's energy system in both net zero scenarios. Because after around 2035, the sector becomes the electricity sector becomes a sector with negative emissions through the use of bioenergy with carbon capture and storage, achieving about 35 megatons of emissions removal from the energy sector, from Canada's economy. So we project that the net negative emissions from the electricity sector actually helps to achieve net zero emissions in Canada by 2050, because as I show in this figure, the whole economy decarbonizes significantly, but there are some sectors that remains. Sectors like waste and agriculture, and then some transportation. Those are what we call like hard to decarbonize sectors. So there will still be some residual emissions, and those net negative emissions from the electricity sector, along with some other emissions removal technologies, helps to achieve complete decarbonization, to achieve net zero by 2050 in Canada. So with that, I'll conclude, and then I'm happy to take any questions if you have. Thank you all.
Thank you very much, Ganesh. Really interesting, and also seems really relevant. Also really like that scenario distinction between Canada and also the rest of the world as relevant input for Canada's energy system. And I think there are a couple of questions. to you. I see one question of Tom.
Yeah, sorry, I don't want to dominate all the questions, but it's very interesting to see the study. Did you have a look at the transport of other commodities or hydrogen pipeline transport, or did you resolve also the CO2 transport and sequestration, like the pipelines you would need to bring the CO2 to the sequestration basins and that kind of thing?
We did, Tom. Thank you for the question. Yeah, we have. We did not. I mean, in the implementation in 2023 implementation, we did not have transportation pipelines, but actually we are working on that currently. We don't possibly be ready for the next iteration of our implementation. So at the moment, we treat the transportation pipelines as like an exogenous input, assuming that would be available. So we only take into account the cost associated with transportation of CO2 and hydrogen, not necessarily the actual physical flows.
Okay, thank you.
And Michael Johnson, as quick as possible, please, because we're slightly delayed.
Super. Thanks so much for this. I'm from Canada, so that was nice to see. I'm curious about the model, the PyPSA part of the model. Is it available on a GitHub? And also, like, is it integrated potentially in the future with the PyPSA USA? I know there's been a lot of work there, and there's a lot of interconnections. Is it, so I guess generally, like, would it be available?
The model code is not yet available in the open domain, but any information that we feed into that, most of that is available through our data portals. If you are interested, please reach out to us. I can lead you to where they are. But like I said, the code is not yet available on GitHub.
Thank you.
Thank you very much, Ganesh. So as our next speaker, we have Carlos Fernandez from the University of Liège. Carlos is currently pursuing his PhD and focusing on modeling long-term energy transitions, especially in countries of the global south. And for this purpose, Carlos prefers to use open source models such as PyPSA-Earth. And today he's going to present a version tailored to the Bolivian electricity system. And yes, Carlos, you are welcome and free to speak up and share your slides.
Thank you. Can you hear me?
Yes, loud and clear.
Okay, great. Now, can you see the screen? Yes, I guess so, right? So, I don't know if it's, can you see the slides? I guess, okay, great. Okay, so thank you for the presentation and also for the time to actually present our testimony on how we actually did what we did. So yeah, I'm gonna present the PyPSA-BO case, or how we used PyPSA-Earth to create a curated version for the Bolivian electric system. And to present this, I think it's important to provide a little context. I am part of 3 PhD groups that is funded by the Haast Cooperation Agency, that it's working with a project with the same objective as the name, which is tailoring energy models for Bolivia. So basically, we want to use different tools to provide and facilitate this transition process for the country. We're working in the Integrated and Sustainable Energy Systems group led by Sylvain Klein, and we're from the University of Liège and UCI. Each of us has different aims, but again, everything is based on this global objective of tailoring energy models. But in my case, I'm trying to tackle the issue of how can energy planning be facilitated for the countries. And like a spoiler alert, the main answer for this is open source models. And what we actually done so far is try different tools to do different things. So for instance, we used Osmosis to run some long-term investment planning in the country, and we also used Dispasset to analyze the dispatch on different scenarios for the country. And both of those gave us very interesting results, but we actually found that PyPSA, which is the tool that everyone here loves, kind of do both of them combined, and it provides a new perspective on how to integrate these two things together. So we said, okay, let's jump into using PyPSA. But actually, we didn't use PyPSA. We used PyPSA-Earth. And PyPSA is like, I would like to say a kid from PyPSA. But I'll explain a little bit about this. So PyPSA-Earth is a model that comes from PyPSA meets Earth, which is an initiative. And PyPSA, it's an open global independent research initiative, which has its mission as to accelerate and cost optimize the world's transition to sustainable, accessible, and reliable energy with open source planning tools and open data. They work in a lot of things. They do solvers, energy models, data, and user development communities. They tackle a lot of things, and they are not paying me to say nice things about them, but I really think it's a cool thing that they are working on. And the team is composed of a lot of people, professor, professional researchers, PhD students, bachelors. I just steal this picture from a slide they have. And yeah, you might be able to recognize a bunch of faces from them. But all of them really cool, really nice people, very open to work with. Okay, so PyPSA meets Earth initiative has a lot of developing tools, and I think the main ones are PyPSA-Earth, which is in short terms a global range energy electric model. They also have PyPSA-Earth-Sec, which is a sector-coupled version of PyPSA-Earth, and then PyPSA distribution version to analyze the small-scale systems. But what we actually found and focused on was PyPSA-Earth, because we already had the information for the electric system. We already did some runs with other two tools, and we wanted to see what were going to be the results if we did the modeling process with a PyPSA tool. So PyPSA-Earth is basically an open source energy modeling system. It's based and developed upon PyPSA, so it uses the whole framework, or part of the framework, and a lot of data management in between. It has a high temporal and spatial resolution and uses a customizable workflow to function. So pretty much whatever everyone has been saying so far. And I won't go into details that, but what can you do with this tool? Basically, you can run your country or region, a lot of countries around the world. It focuses a lot on power system representations and analyze it's used to analyze expansion scenarios. So here are a couple of pictures that you can actually see of the results that you get from using PyPSA-Earth and trying to apply it to a country or a region or an entire continent like Africa. But again, this is what they have in their documentation webpage. You can go through it. How does this model does all of that? It basically does a lot of data collection from different sources regarding infrastructure, environmental data, and socioeconomics, compiles everything into nice bundles of data, and uses PyPSA to formulate an optimization problem that is then solved with an external solver. Okay, so that's everything that it's out there. So what we actually did, we stumbled upon PyPSA-Earth, thought, okay, this is cool. This seems like a very interesting thing to do, and let's try to run it and see how what happens. And this is actually the result of this first conference paper that we published last year, which was basically, let's try to use PyPSA-Earth as it is and try to run Bolivian. Results were quite interesting, actually. We, of course, didn't have the best data set of information regarding lines and everything else from the pre-Klein data source that it's using PyPSA-Earth, because in a lot of developing countries, data is not updated or available. But we were able to tweak a little bit the model to have a representation of the system that kind of matches the Bolivian system. And the results from, say, the problem of how they cluster demands were actually quite good compared to the Bolivian. Again, a bit of a discrepancy between, but the structure kind of is the same. So it seems very promising. Of course, there's a lot of issues with data, but we'll see what happens. That was the main outcome of the paper. Nice, works, but needs better data. And because of that, we decided to work a lot in the data. And because we integrated a lot of our own data, we decided to just say, okay, it's not PyPSA-Earth because we're tweaking a lot of things and we cannot push everything that we're doing. So let's just put a new GitHub with all the scripts that we're modifying and the data sets that we're using to present PyPSA-BO, which is an application of using the same workflow that PyPSA-Earth uses and just tweaking a little bit what type of data it's taking and maybe replacing or improving the data that it's using as a default from the sources it has. From there, we actually managed to represent in a better way the Bolivian country, at least at capacity levels for power plants. And we were able to start running more interesting scenarios and saying, okay, it kind of runs or maybe it doesn't. Here you have the results from a paper we presented this in January. In Chile, it's a conference paper where we showed how we could simulate the dispatch and the effects of having a high or low availability of inflows for different power plants and how would that affect the energy system in Bolivia. So if we have low availability, then how is that going to impact over the dispatch in the system in the long term? And we run some expansion scenarios and so on. But now, basically, the work is running because we were able to update a lot of things in this very, very nice tool that it's open. And I think that's the key word when we're trying to adapt tools to developing countries. It's open, it's transparent, you can get to the information, you understand how and everything, what's happening around. So, okay, that's what we did so far, but of course, there is more to do. We want to explore additional scenarios. So far, we've been toying around with very simple alternatives, but we want to, let's see, transition net zero to 2050 on steps on what happens if availability of resources not only changes for hydro, but for other resources. And yeah, there's a lot of things that we want to see into the future. And I think that this tool can actually help us a little bit to see what might happen. Then we also want to focus a little bit more just on the transmission system, because so far we've been using whatever is there. And of course, we need to tweak that. We had some mixed results, but it's definitely something that we can solve. We also want to do some interaction between tools. We know that PyPSA is doing this, which actually turned out to be something that we model with 2 other tools, but we want to integrate maybe an integrated assessment model also into the mix. And of course, we want to contribute, keep contributing to the development of PyPSA, and we were able to push actually a pull request where we presented the idea, okay, so you have these data sets, you can maybe add an option that allows you to use your own data sets instead to just mushing the code and pushing your information. Of course, there's also much more to do with PyPSA-Earth. I presented in rough lines the work groups that they have, but yeah, just jump into the documentation webpage links. There's a lot of information there. And also, if you're working with Latin America and doing some country case studies, I would love to hear from you. So yeah, thanks again. I think I'm over the time, but yeah, thank you.
Thank you very much, Carlos. I think you just showcased one country of the numerous countries that you can already model with PyPSA-Earth. And I also can fully confirm your statements about the kindness and the competence of the PyPSA-Earth community. Maybe let's have a look into the questions. I see one question from Alice. Do you want to speak up?
Yep, sure. Thank you. So thank you, Carlos. That was very interesting. I agree so much on the fact that since it's an open tool, it's very powerful for developing countries. And yeah, also the idea of checking hydropower is very interesting, because I think that climate change can put a very high risk on some power systems that are very relying on this source. So I was wondering if you also consider the correlation that there might be on reduced hydropower and increase in electricity demand, maybe because of course, electrification of transport and all this kind of stuff. Thank you.
Okay. Yeah, no, thank you. So for this case, we actually just analyzed historical data of how hydro is varying across time. So we're seeing a downwards trend in the availability of hydro. Like, it's small, but it's still a trend, like 1% reduction each year. And then we also saw like extreme events like El Nino. So we decided to project everything until 2050, demand growth, electrification rates, and so on. And then try to run everything with these two alternatives. Like what happens if the overall availability reduces and it changes between the El Nino case and average year. We didn't do a mix or actually an analysis regarding hydro and demand specifically, but yeah, it should be easy to do. And if you're working on it, I would be very glad to keep talking about it.
And I see another question from Matthew Dumlao.
Hello. I'm just curious how you handle the hourly data, because you showed that you have the data for the annual data, and then we have to disaggregate that to hourly level, right? So could you explain a bit about that one?
Okay, so there are two options. PyPSA-Earth already has a predefined hourly profile that you can use based on shared socioeconomic pathways, and I'm not entirely sure what's the other source, but you already have a predefined demand profile for the entire country or for the entire globe. So you can just use that demand profile. But I thought it was kind of not good for the actual characteristics of Bolivia, which are quite different to the average profile. So for that, we went into the TSO webpage and tried to download the dispatch of an entire year and try to accommodate that profile to the data structure that PyPSA-Earth uses. So basically, we just created a load profile and swapped the files.
So in the end, you have the data from your own TSO, right?
Yeah. I mean, we had to work a little bit for it, but yeah. I mean, if you want to have a realistic scenario, you need to do that.
All right, thank you.
Oh, thank you.
Okay, great. I think we're slightly over time. I'm seeing a couple of more questions, but maybe we can just ask them in the dedicated breakout room that we will have afterwards. So then there would be time to move on to the next speaker. And we would like to welcome Rowan Tunnicliffe from Mutual Energy. Mutual Energy is a mutual TSO from Northern Ireland. So that means the company is limited by guarantee. Really interesting approach where they own and operate strategically important energy assets on behalf of the local Northern Irish energy consumers. And among these assets are the interconnector links to Scotland for gas and electricity. Today, Rowan is going to explain how Mutual Energy approaches security of supply questions using PyPSA to ensure future-proof planning of the TSO asset base. And Rowan, I'd like to give you the floor.
Hi, thanks. Sorry, let me just get my screen up here. So I'm used to Teams, not Zoom, so this might take me a minute. Can you see that okay?
Yes.
Yes, right, okay. Yeah, so I think you've already covered some of my introduction there, to be honest. Sort of explaining who Mutual Energy is. So yeah, we own sort of strategically important assets for Northern Irish consumers, including the Moyland connector between Scotland and Northern Ireland, and the natural gas interconnector that connects Northern Ireland to Great Britain, as well as a lot of the onshore gas transmission network within Northern Ireland. Like you say, we're a mutual company, so we don't have any shareholders or anything. We're sort of set up entirely to focus on managing the assets in the interests of consumers. And to date, we've saved about £200 million in sort of financing costs through that approach. But as part of that approach, I suppose one of the things is making sure that what we're doing is cost effective, and we're not sort of spending consumers' money on where we don't need to be. So that sort of played a part in us looking into PyPSA as a solution for our modeling needs. So I suppose in terms of a bit of history as to why we started looking into our need for modeling, I suppose in the short term, as a gas TSO, we have different obligations placed on us under our license. So managing the network efficiently. If somebody wants to come and get a connection, say for a new power station, being in a position to do that within a certain time frame, and making sure that we manage the sort of gas market efficiently. With the energy transition coming along, though, that our role in that is changing. So, for those of you who are familiar with Northern Ireland, you might know that there was a big coal power station, which was decommissioning towards the end of last year and switching over to natural gas as a fuel. So, sort of as part of our annual forecasting, we identified that we were going to sort of start seeing congestion on the gas network as a result of that. To date, it hasn't actually materialized just because that was delayed, and it only actually started using gas last week on a commercial basis. But going forward, we do expect to see the gas network is going to be under more stress than it has been historically. And then I suppose the flip side of that is, well, as I suppose with electrification coming along as well, we're expecting that overall gas demand will start dropping off, but the peak day will start exceeding what we've seen historically, because the power stations that we're seeing are going to need to be there as backup when the wind doesn't blow. But on the flip side of that, I suppose Northern Ireland and Ireland in general, so I should say, the electricity system here is an all-island market. It's fairly world-leading in the amount of wind energy and solar, to a lesser extent, energy that it's bringing on. So there's very few places in the world that have as much wind energy at one time as Ireland. But what we're starting to see with that at the minute is that because there's so much and there's more connecting, that there's a significant amount of oversupply. So as that electrification grows and more renewables get installed, that problem is going to become more severe, and basically a large chunk of the generation potential is going to be wasted. So we're seeing hydrogen as a potential solution to that. And the other side of things is biomethane potentially could play a big part. I mean, Ireland and Northern Ireland, they're very sort of agricultural focused in terms of the economy here. So as part of the decarbonisation effort, using the methane that's there and emitted by the agricultural sector and doing something with it and capturing the carbon potentially is going to be a big part of our pathway towards net zero. So that's a bit of backstory about why we started looking into this. I suppose in terms of our models, in terms of managing the gas network, we have this hydraulic gas model, which allows us to look at pressures and flows on the network on sort of a transient basis. But as inputs to that, we need to know how much power stations are going to be demanding and how much distribution customers will be demanding for heat, etc. And obviously there'll be an interaction going forward between heat demand from distribution and heat demand through the power sector as things potentially get electrified with heat pumps rolling out. So we were looking very much for this power dispatch model that we could use to sort of feed into the hydraulic gas demand modeling. And we were sort of considering two options. One was PyPSA and one was Plexos, which is sort of the industry standard. I suppose PyPSA won out for a couple of reasons. One is it's open source. So as I say, we're sort of part of our ethos is minimizing costs for consumers. So that was a big driver. The other side of it is it allows us to sort of get into the nuts and bolts of what the model's doing, whereas Plexos is more of a black box. So I suppose we wanted to sort of get in there and look, see, why are things happening, rather than just take the outputs and say, oh, okay, that's fine. We wanted to know why. And I suppose the one benefit which Plexus had was it has sort of customer support, but obviously PyPSA has a very active user community, as demonstrated by today. So that was less of an issue for us. So that's how we ended up at PyPSA. And then within that, we built an electricity model of the all island market and the network here. So it's a two-stage model. The first is it's a market-only model, which is sort of a copper plate type approach, where there's a single node with the generators connecting. We feed in wind, solar profiles, commodity prices, etc., and load profiles, which spits out prices and interconnector flows, which obviously as an owner of an interconnector, one of two current interconnectors between the all-island market and GB, that's of interest to us. And then subsequent to that, we have the dispatch model. So the electricity TSO in Ireland and Northern Ireland publishes a lot of very detailed information in terms of line and transformer ratings, and that's all there in the public domain. We had to make some assumptions around locational wind generation and demand profiles to sort of feed into each of the nodes. But what we could load into it then, and this, I spent a lot of time on this, is the electricity system operator puts a lot of system constraints on. So foremost of those is this SNSP, which is system non-synchronous penetration limits. So like I say, there's a lot of renewable electricity in Ireland, and at any one time, there could be 100% of load being met by it, but because of thermal reasons on the network and needing inertia and that sort of thing, and the system operator needs a certain amount of spinning plant on the system at one time, and that's currently 75%. So that's wind, solar, but also interconnector imports, and it's overload and interconnector exports. So basically there was a bit of playing around with some code to try and get that in there. And then there's a minimum number of sort of thermal units that have to be on, and that's all fed into there as well. And coming out of that, it allows us to have sort of generator profiles in terms of an hourly resolution, which allows us to basically compute the natural gas demand and feed that into our hydraulic gas model. So in terms of, I've just put up some results here, so to sort of show how accurate our model is. This is 2022 data. I've sort of back forecasted it against, and you can see on average, it's sort of given a reasonable prediction of prices. I haven't shown the dispatch profile on here just because it would have taken up too much room, but it gives a reasonable forecast for what we expect to see in terms of dispatch from particular power stations as well. Now, it's not as spiky as the actual price, which there's a couple of reasons for that, which I suppose first and foremost is it doesn't take into account sort of assetless traders who participate in the market. And it also only takes linear cost curves, whereas a lot of generators would bid in non-linear, which is a sort of potential improvement we want to add in. But on the whole, in aggregate, it gives a very reasonable forecast for what we see on the electricity system in Ireland. And in terms of the interconnector flows as well, it gives a sort of, over the course of the year, very good estimation. So I suppose in terms of future plans, one thing that we want to do is sort of, and I think Andrew had mentioned in his talk, GB, the system operator there, produces the future energy scenarios document, and the system operator in Ireland does a similar document as well. So that's all based on expansion modeling and capability. So we want to sort of add that into our model and interact hydrogen and electrolysis on the demand side with the power system so that we can see how much hydrogen there's likely to be needing to be moved around, and where and how much storage would be needed. So Northern Ireland's actually very fortunate in terms of hydrogen storage, and it sits on top of a big salt layer. So salt cavern storage is very technically feasible in Northern Ireland, and there's a large amount of it, more than Northern Ireland itself would need. So it could support Ireland and GB in terms of their storage needs as well. Like I say, we want to convert to quadratic cost curves as well for the dispatchable generation. Just when I first built this model, that wasn't a function that was available in PyPSA, but I know it's there now, so it's on the to-do list. And then there's other sort of add-ins that we want to make to the dispatch model as well. But I suppose in terms of doing a sort of long-term scenario-based forecast, there is potential collaboration there with academia as well and other sort of system operators and industry. I suppose we've been part of the Highlight project run by Dublin City University, which I know uses PyPSA as well. And that sort of approach is something that we would be looking at going forward. So I might be over my time here, but I suppose that's my contact details as well, if anyone wants to get in touch. But yeah, that's me.
Thank you very much, Rowan. Really interesting, and seems as if you yield some really decent validation results there. Really good accuracy. Yeah, actually, I don't see any questions. I would like to take advantage of that to move on quickly to the next speaker. There's only one comment from Tom, which could be interesting for you to pair up with SEAI.
It's the Sustainable
yes.
Energy Authority of Ireland. They have to beef up some of their modeling capabilities at the moment. So if you're not, I'm sure you're in touch with them already, but they are definitely interested in PyPSA or our other tools, so they may profit from the model you've already built. Just a comment.
Yeah, no, that's really useful. I am aware of them. I've never actually met them, but yeah.
I can pass on your details to them. I'll do it by email though. Thanks.
Sure. Oh, brilliant. Cheers.
Okay, thank you very much, Rowan. Then as our next guest, we have Tom Welfonder from the University of Stuttgart. His research group developed an application for optimizing the unit commitment of a waste-to-energy plant for the day ahead and the balancing energy market. And this involves the implementation of the respective market and bidding mechanisms. And they also followed a stochastic optimization approach, taking into account uncertainties for market prices and also for heat loads. And now we're really curious what you have to tell us, Tom. The stage is yours.
Hi, thanks. So I'm gonna real quick share my screen. Okay, I think it works. Okay, we did stochastic unit commitment on multiple power markets using PyPSA. Here is a quick overview what stochastic unit commitment is about. The goal is to obtain an operating schedule here and optimal market bids under uncertain prices for the day-ahead market or the balancing reserve markets, and also for uncertain constraints for your power plant, for example, the district heat demand. And we implemented all of this inside PyPSA. For example, we modeled the balancing reserve stochastic optimization, and we modeled market mechanisms for the day-ahead market and the automatic frequency restoration reserve markets within PyPSA. And for the optimization, we implemented multi-staging and a rolling horizon. We applied all of this to one example power plant, in this case, a waste-to-energy power plant with two storages, one electricity storage and one heat storage. And here you can see the results for the negative restoration reserve market, you can see as dots represented here the bids that were placed and the corresponding actual market price. And marked in red and green, you can see whether a bid was accepted or rejected. And as a result, you also get an operation schedule. Here, for example, the schedule for the state of charge of the electricity storage system. And you get these operation schedules for each stage. The first stage is for the balancing reserve market auction. So in this case, there are 4 uncertain time series, namely the day-ahead market price, the positive and negative frequency restoration reserve price, and also the district heating demand is uncertain. And in the second stage, that represents the second market decision, only the day-ahead market prices are uncertain and the district heating demand is uncertain because the results from the auction before are already known. And in the last stage, all time series are known, or and this stage only represents the optimization of the operation schedule itself. To explain stochastic optimization easier, you can at first look at a regular deterministic optimization for a linear problem. So here you can see a general way how you can write a linear optimization problem. The goal is to minimize a linear cost functional under some linear constraints. And if you want to you want to transform this into a stochastic optimization, you replace the cost function with the expected costs. So what you have to do, or what you can do, is you create your model for each scenario, and then you modify the cost function to also take all of these scenarios into account and weight them with their probability. You also need some additional constraints. In this case, for all scenarios, they have to use the same bids because they have to have to conclude to one bid that fits for them all. We implemented all of this in the PyOmo framework, and we're going to implement this we're going to work on implementing this for LinearPy in the future. We did most of the things within PyPSA. One thing we did outside of PyPSA was creating the scenarios. So the predictions and forecasts was made outside of that. But we used PyPSA for most of the things we did. For example, the modeling, most of the modeling part was done within PyPSA. We used native PyPSA components to model the power plant and the storages. And so the main base component of the optimization is a basic PyPSA network, which is created for each scenario. And we used extra functionality to model the balancing reserve, to model to implement stochastic optimization, and to model the market mechanisms for the day-ahead market and the restoration reserve market, and also for multi-staging and the rolling horizon. And each of these extensions can be used independent of the others. So if you want to model balancing reserve markets, you don't need to implement these or use this part for the stochastic optimization. So these are really independent. why we used PyPSA, because when you use PyPSA, it's quite easy to extend your existing model by using existing PyPSA components, which are really convenient to implement, for example, battery storages or heat storages. We also implemented an example for power to X. And in the future, we see some opportunities by using PyPSA with functionalities like investment optimization, or you could use PyPSA to analyze some large networks. If you want to know some more information on our project, you can find our project, the code, on GitHub, and you can also find a preprint with the link below here. I'm gonna post these links also in the chat. Okay, thanks for your intentions. For your intention, and if you have any questions, just ask them.
Thank you very much, Tom. Also, thank you very much for being so fast, or keeping it exactly as it should be. Very interesting. Also seems to align pretty well with some ongoing research at TU Berlin. And I'm seeing one question from Ali Tash.
Yeah, thank you very much for the very interesting presentation. I have a question regarding the stochastic modeling. So is it a type of Monte Carlo modeling with a lot of deterministic solutions, and then you weight every solution with probability, or can you explain a bit more about that?
Yeah, I can maybe show you one slide. It's a ARIMA model, and then you create many, I think about 1,000 deterministic scenarios from that. And then we used k-means clustering to obtain five scenarios weighted with their probabilities from these 1,000 scenarios. And we created 5 scenarios for each forecast.
And then you calculated every scenario?
Yes.
Okay.
Or every combination of these scenarios.
Every combination, okay, yeah. Thanks.
Then I see one more question from Tapio.
Yeah, I would be interested. I remember some uni projects implementing multi-stage stochastic optimization, and solving time explodes quite quickly. Like, how do you cope with that? We, for example, implemented this L-shaped method, which is a kind of Bender's decomposition at the end, which was quite specific always to the case. I don't know, how do you cope with this issue?
I also had that issue implementing the stochastic optimization, especially if you want to use more than, let's say, 5 scenarios for each forecast. It's most of the time already too much to calculate. Implementing the L-shape algorithm would be one thing to improve this, but we didn't have the time yet to try something like that.
Thank you.
No problem.
Great. Then I would go on and introduce the next speaker, but our next speaker also raised his hand, so I would also, out of politeness, ask Shuwei Zhang to ask his question.
Yeah, that's maybe the question relevant to the first one. So what kind of storyline or uncertainty factor you consider in such a stochastic? Because you stand on the day ahead or uncertain, or which uncertainty factor you are factoring in?
Could you repeat the first part of the question? I couldn't.
That's maybe relevant to the first question. So which uncertainty factor in your storyline? So the storyline you stand in front of the day ahead, so there everything is certain. So you say which part of the picture of the market is is uncertain. It's with what kind of probability distribution?
What probability distribution we used for which prediction model, or what is? I still don't quite.
Which parameter or which variable? Which one you think that's still in randomness? That's not decided.
The question is like, where's the uncertainty on the demand or the wind and the solar? Where is the uncertainty and what's the probability distribution? I think is the question.
Ah, okay. Sorry. Yeah, in this case I think what might be an answer to your question. For us, we thought that in our case, the market prices were uncertain and the heat demand, and we created these forecasts using forecasts for the solar and wind power generation from the NSOE, and we also used some forecasts from for the load forecasts, and then we assumed a normal distribution for the heat demand, and for the electricity prices we used a transformation, so the sinus hyperbolicus in this case, and this would mean we assumed in this case that the prices were log normal distributed, or kind of log normal distributed, and yeah.
Thanks. I will read your paper.
Okay, and then Shui or Xuanzhang, you're then also free to give your presentation. Many thanks, Tom. Was really interesting.
You're welcome.
Yeah, Sean, you're chief energy economist of a boutique research center, Drawworld Research Center in Beijing. And according to my research, you do research and consultancy with respect to many two areas. So first, digitalization of the Chinese energy sector, and also second, about the nexus of China with the rest of the world. And today you're going to speak about Drawworld's power system model, in which Drawworld aims for a close representation of the highly regulated and dispersed system using PyPSA. So the floor is yours.
Thank you, Caspar. Thank you for including me in this discussion. Yeah, if you can hear me clearly, I will start with my long title again. So there will be 3 keywords. One is the heterogeneity. So by its nature, the world is heterogeneous. It's different corner with different patterns in the good or bad way. So here. And the second one is transparency, as mentioned by some colleagues. Yes, in such a highly regulated system, maybe the hourly load is not publicly available yet. And why we use the de facto 33 balance area? That's because, yeah, in most cases, such a way is holding. Yeah, but in exceptional cases, that's not such one. That's not stable and absolute. We will see details later. So I will talk about these 4 aspects. So how we applied the PyPSA into our so-called energy reference energy system, RES, and to apply it to some our consulting research and project work, and the specific questions we tackled and are tackling. I will summarize with our findings and expectations on PyPSA expanding. Yes, so basically our RES system is admittedly is a reduced form from the powerful PyPSA with a very complex node and edge system with different components to constitute the network. Basically, our is still a power sector model. It's just with a balance of the electricity demand hourly. So in terms of a special dimension, that's 33 balance areas. That's generally province in China. There's two exceptions. One is surrounding Beijing, that's so-called North Hebei. They are responsible for the security of the capital electricity demand. Another one is a very wide and Inner Mongolia. It's split in the middle, that's more or less that's belonging to different jurisdiction of the great companies. So basically, in a nutshell, the role of PyPSA in our efforts, that can be such a role. The first one is with relation tools. Yeah, we can use it as to visualization the latest operational patterns across various provinces. With our calibration, let's try to close to the real operation as possible as we can. And for future, with such modeling, you can get some insights on the findings. The second one is a macro level analysis. So in terms of the system patterns, like its energy efficiency, the net co-generations, the capacity of different technologies, and the potential bottlenecks. The third one is emission accounting. So that is one of our central tasks. Maybe you know or know already that China have a power sector only emission trading system. So we put some efforts in this sector to connect with that data system and try to match them in a possible way. So the fourth one is we have some research topic that's China specific one. So we try to identify what was the unique regional challenge and patterns across the whole country. So the example of our work, the first one is about the EV behavior. So-called smart charging. I think just 2 or 3 years ago, people still think charging in the noon is a good idea. That's the reason is very clear. That's in the noon, the solar PV is planting off. Also, the solar PV is cheaper and very cheap now. But actually, such one is more and more challenged by some people, because if you move your focus beyond the generation side, you move to the grid side. In the noon, that's easy to have the congestion in the distribution grids or even the transmission grids if there's no enough buffer. So in the left, there is a study in the US, California. So they argue not charging in the noon, but charging in the early morning and midnight. That will be the smart charging. But I follow such a logic. If you extend the system boundary further, that will be maybe another picture again. If people just incentivized to charge their EVs in the earlier morning, so that means they were congested in the parking slots. So the parking slots will be with the most limited buffer. So there. So from such a intuition, that's maybe the robust strategy in terms of EV charging. That must be distributed evenly and enough. So such a system will be better to adopt to the very huge capacity demand of EVs with obvious size. So that's consistent with one of the British and German economists, Herr Schumacher. He said, small is beautiful if people really mentored. Yeah. So our work is just show the objective function of the PyPSA to consider a various system boundary. We argue, yes, the charging is largely self-defending, and to say if you concentrated in one segment, in one time moment, that means easily it will be congested in a very short time. But it's a totally different picture if you consider V2G. Yeah, because V2G means if you do that, you can get revenue from that. If part of the EV owners do that, they will raise the charging price of the others, and will be promote the others to join as well. So basically, the V2G will be a self-fulfilling phenomenon here. This is one example. Another one example is the coal issue in China. So basically, the status quo now, it can be summarized that the coal cannot be up enough because of economic incentive, because of the suppressed price. Also, it cannot be down enough because that's by design. Its minimum output level is quite high. So we can build some counterfactuals to test many what if scenarios. I think you already understand what I mean. So I will skip here. So if such a constraint didn't exist, so what's the consequence on the system performance, on emission patterns, and all on the others, on the role of other technologies. So the third one is heterogeneity across the provinces. So naturally, they are quite different. For example, some provinces like Qinghai, its load curve is still almost straight. So under such a case, you will not bother to say, so what's the best data for its load? It's a straight. It's an industry-dominated one. But in some coast area like Zhejiang and Jiangsu, that's more like the situation in Europe and the US. Also, there are some special cases in the middle China. That's there. There's wind weather is quite special. So they have a peak period in the winter. So always every day that's some difficult moment for people to cope with such a balanced challenge. Another special pattern is about the transmission lines again. That's also I think someone already mentioned that the China's grid, there's many privileged electricity transmission. So how to consider that? How closely you model that? Yeah, to the real power flow. That's really a question. Sometimes we bother that. Sometimes we didn't bother. But in some cases, that cannot be ignored because it's huge simply. So, for example, so there's a case to assess and to evaluate the system adequacy of the Zhejiang province. It's out inflexible transmission could be 1/3 of the total there. So that must be considered. That's so in some way, but actually in the real operation, it's descriptive operation. So how to handle that? Yeah, that's our challenge. Yes. So basically, to summarize and finish my presentation, that's I think our modeling aligned with the operational reality of China's power system. To what extent we closed that's a critical concern. For example, we must consider the inter-year transition projects because the projects, if you are put into operation in the middle of the year, that means your operation hour is only half or less than half of the exogenous setting hours. It sounds like operational trivial issues, but if the volume is very large, that means you must deal with that. Overall, we are already derived a substantial benefit from employing the PyPSA. It's like a general purpose tool for us. So our understanding is still focused and narrow, but we are eager to exchange with you further and to learn more. Thanks.
Thank you very much, Wei. Actually, in the chat, there's one remark of Tom where he posted a link of another PyPSA model for China. So that could be interesting for your hydro modeling. And yeah, otherwise, I would also like to take the opportunity to move on fast because I'm already feeling really guilty for my mediocre time management. because we have one last but not least speaker, Adrian Odenweller from the Potsdam Institute for Climate Impact Research. Adrian is currently pursuing his PhD, focusing on sector coupling and the assessment of the roles of electrification, hydrogen, and PTX synthesis. And today, Adrian is going to tell us something about the model coupling concepts that he has followed to couple REMIND, a quite prominent integrated assessment model of PIC, and PyPSA-Eur to combine the strength of these two open source models. So thank you again, Shui. Sorry, Adrian, and curious to hear our last talk.
Sure, no worries. Let me share my screen. I hope you can hear me well.
Yes, we do.
Okay, cool. So yeah, thanks for the kind introduction. I'll try to be quick. So I'm Adrian. I'm a fourth-year PhD student at the Potsdam Institute, and we've been working on coupling our integrated assessment model REMIND, and I'll explain in a second what the heck an integrated assessment model is, to PyPSA-Eur. And I'm presenting this on behalf of the list of authors that you can see here. And you might see, well, one of those names might seem really well known to you, and that is Johannes Hamp, who I believe was quite prominent in the PyPSA user and developer community, and who was also with us for 8 months at PIC, and quite pivotal in moving this on. Now, as I said,
Adrian,
yeah,
I don't want to interrupt, but in case you already want to show us something on the slides, they're still not visible.
Nothing to see. Well, it was just my. I did click share screen, didn't work. It was only my overview slide anyway, but there we go.
Now it's working.
Okay,
perfect.
Just did it again.
Thanks.
Cool, no worries. So what the heck are integrated assessment models, right? And I just want to briefly advertise the kind of modeling that we do at PIC, which is integrated assessment modeling, which is quite pivotal for example, the IPCC, as our scenarios essentially underpin global climate negotiations. So integrated assessment models and the pathways of those are essentially the methodological core of the Working Group 3 of the IPCC, and therefore also pivotal for climate negotiations. We also have different, well, let's call them impact channels maybe. And for example, our scenarios are also used by a consortium called Network for Greening the Financial System, NGFS, which is around 130 central banks across the world, which also have scenarios from us and from other institutes that explore the impacts of climate change and policy, and which actually get downloaded a lot more. Now, looking to the IPCC very briefly, these are the number of scenarios from models submitted to the IPCC in the last assessment report 6. And we're a bit proud to say that our REMIND model is here on the very left. So it's the one model that has submitted the most scenarios across the AR6 database, and not just the most, but also those with a really high share of essentially vetting, which is some kind of consistency check with recent historical developments. Okay, so I think it's fair to say that IAMs are quite influential for climate policy making, but it's probably also fair to say that they are not very well suited to model future power systems. And that is mostly because our spatiotemporal resolution is really low. And that's what we now really want to do, is really to leverage and harness the synergies of IAMs, which CLR in the orange box on the one hand side, and power system models on the other side. This is quite simplified and stylized, so please bear with me, and I hope you don't feel offended. And I still find it illustrative to just highlight that integrated assessment models are really, I think, good at things where power system models tend to be, well, at least in need of exogenous parameters, like for demand or cost parameters. And on the other hand, for example, integrated assessment models have really low spatial and temporal resolution. So our REMIND model runs in 5-year time steps up until 2150, which is obviously not sufficient to model anything related to the power sector. However, then we have a really high spatial and temporal scope. So we run an intertemporal optimization across to 2150. We have all regions across the globe, elastic demand, and all these kind of things. And I think it's really promising here to really try to leverage those synergies, with the key idea is then that integrated assessment models take care of global long-term pathways and are then added by power system models, which provide hourly power system dynamics and also, grid effects and so on. Now, which kind of models are we talking about here? I don't need to explain the right-hand side to you, I believe. So I just added this nice little picture of PyPSA-Eur. We only use the power sector from PyPSA-Eur. And on the left-hand side, we have REMIND, so our own integrated assessment model, which, as I said, runs in 5-year time step, actually later towards the end of the century, even 10-year time steps. And it's integrated because it integrates a macroeconomic core with an energy system that has a simple representation of variable and dispatchable power, also transmission and storage, but really nothing nearly as good as what PyPSA-Eur offers. However, REMIND is already coupled to a bunch of other models, one prominent of them being energy service demands for the transport industry and building sectors. Secondly, also, we have a dedicated land use model called MACPY, and we also can couple to a climate emulator, so essentially a low complexity Earth system model called MAGIC-C. And now we want to add another layer of complexity to this by adding, or by coupling to PyPSA-Eur. And how do the models now talk to each other? So what we give from REMIND to PyPSA in terms of input are 3 things. It's first of all power demand, which we use to scale up and down the load time series as a first approach. Secondly, all kinds of technology costs, so CapEx, OpEx, efficiencies, carbon prices, you name it. And then thirdly, also minimum capacities, so that we operate PyPSA-Eur in a kind of brownfield way. We then run PyPSA-Eur 15 times, so 15 networks in each iteration. So 15 times because, well, for each time step of REMIND, we run a single, we solve for one network of PyPSA-Eur, so 2025, 2030, and so on. And we then aggregate all these results and pass them back to REMIND. And what we pass back is most of all is market values. So the electricity price that a generator receives aggregated over the course of the year. Also aggregated capacity factors and residual peak load. So how much residual peak load do we have that needs to be covered by dispatchable generators? And the key idea now is that this goes on in an iterative cycle until both models make the same endogenous capacity investment decision. Just briefly, we've run this for a proof of concept scenario setup so far, so I'm not going to show some very exciting results yet, but they are about to come. They are in the pipeline. So, and for this proof of concept scenario, we use a global baseline, so current climate policies in REMIND, and we use PyPSA-Eur version 0.9. As I said, electricity only, Germany only 4 nodes, so very simple. Storage and grid expansion are on, and in a brownfield way where we, as I said, give minimum capacities from REMIND to PyPSA-Eur to mimic the inertia in the transition. Very briefly, convergence of capacity investment. Now what you see here is capacity over time, and for each time step you always see 2 bars. The left one is always REMIND and the right one always PyPSA-Eur. And the point, what we want to show here is that capacity investment decisions actually converge already fairly well. We see a bit of divergence in earlier years towards more PV in REMIND, bit more PV in PyPSA in later years towards the end of the century. Bit more wind in REMIND that compensates for that. But overall, this is already looking pretty good. We're still working on improving convergence, but this is this is at quite a good shape already that we are now probably soon move on to the next steps. Talking about next steps, mutual benefit and research outlook already. So what's in it for REMIND? So, I mean, we've set this up essentially in the way that we want to improve our own power sector modeling. And I think that really it does a great job at that. And then essentially we also really hope to provide better mitigation scenarios for, well, at least better informed policymaking and potentially even better policymaking. What's in it for PyPSA? Well, I'd be curious to hear that from you mostly, but I personally think that, well, what we can provide is a consistent set of future cost and demand parameters, consistent in the sense of compatible with a certain climate target intertemporally as well, and perhaps also a cross-check of your myopic pathway optimization that I know is implemented in PyPSA-Eur already. What we want to do in the future, so this is research that we're really expanding a lot currently. We'll actually hire somebody soon whose plan is to expand this to for a PyPSA-China coupling. So first of all now, however, we want to expand it to other European regions, so sticking with PyPSA-Eur for now. And a second step then also to other global regions, for example, using PyPSA-Earth, although we haven't really decided on that yet. That's still, that's still up for discussion. And then obviously also we want to also get sector coupling technologies better represented in this coupling, which for us mostly means getting relative prices, not only on the supply side, which is what we already have, but also on the demand side. So how much do various demand actors pay for electricity? Cool. And I'll leave it at that. And yeah, thanks. And hoping to get some cool questions.
Thank you very much, Adrian. That was indeed fast as a lightning, but still incredibly well understandable. So respect. There are also a couple of questions. The first one is from Tapio. Tapio, you want to speak up yourself?
Yeah, I can. Thank you very much, Adrian. Actually, we've been exactly dealing with this lacking consistency because we were looking at greenhouse gas emission intensity of electricity globally, but then also wanted to assess flexible assets and needed hourly profiles. So actually, we would have exactly be interested in this hourly stuff, but we only found it for Europe from our own model, which then wasn't consistent to IAMs. So we had a lot of problems in that context. So maybe just a general question to you. Would you say that IAMs are still, of course, the capacity of single technologies can change, as you showed in the convergence process, but is the emission intensity of the electricity mix more or less constant, or is it even sent exogenously from REMIND now in your coupling to PyPSA, or how is that dealt with?
Yes, that's what's happening. So, I mean, what we do have is, I mean, essentially, we want to, I mean, in order to harmonize all these investment decisions, you really need to have the same set of parameters everywhere. And for that, we don't only pass costs, but all kinds of techno-economic assumptions and parameters. And that also includes CO2 intensities of various primary energy carriers, however, right? So we pass, emission intensity of coal, gas, oil to PyPSA, and it can then decide, and that essentially that just impacts the operation decision, also the capacity investment decision. But yeah.
Okay, and maybe just to ask a second question, if I may, because we
Sure.
saw this massive amount of BECCS and some IAMs being used very late. Do you have this thing also in REMIND, or was it the other ones? I don't remember in details. I think it was image really exaggerating, but yeah.
That was a very typical outcome of many IAMs until recently, and perhaps even now, I would say, simply due to the fact that in many IAMs, BECCS often had bit over optimistic assumptions, maybe also regarding sustainability concerns. I would argue that we tend to be on the high electrification side with REMIND, and we actually also provided the illustrative mitigation pathway for renewables to the IPCC. So I believe that we tend to be quite good at mimicking and modeling electrification technologies, which then eats away some of that BECCS that is otherwise often deployed in IAM scenarios.
Okay, great. Then we have one more question from Alice.
Okay, thank you. Yeah, Adrian, thank you for the presentation. I wanted to ask you if you had a look at the storage also, because maybe the fact that at a certain point you have more wind or hydro is driven by the type of storage that is usually connected with those technologies. And I wanted also to comment on Tapio's comment on the carbon removal part, that maybe sometimes in IAMs, there's the fact that due to overshoot, then the model needs to stay below a certain level and stay in some sort of temperatures, and then needs to do a lot of carbon removal at the end. So that might depend on like sticking to a certain level of temperature at the end of the sentence. Those parentheses.
Yeah, thanks. I'll answer to the first question regarding storage. So essentially, we did have some parameterized version of storage in REMIND before as well that we switched off, and instead now PyPSA obviously does all the storage, both capacity investment decision and also deployment. And we currently, we don't yet. So what we need to do in order to fully harmonize the investment decision is that we both pass back the additional cost of that, but also the benefit. And right now we're only sort of passing the benefit by the market values of, say, solar or whatever. I mean, storage would increase the market value of variable renewable technologies, but we don't yet pass back the additional costs because we still need to implement these in REMIND as well. But yes, that's something that's also on our list, as are many other things. Yeah, the list is endless.
And the next question comes from Song Min. Should be answerable in a quick fashion. Maybe I just read it out. How long does it take for having convergence for this proof of concept case?
Yeah, I would say that for the resolution that we're at now, the runs take twice as long as they did before. So we essentially tap into iterations that we had in REMIND previously before anyway, because regions optimize separately in REMIND, and then in between we had those iterations anyway, and we just simply use those to feed in additional information from PyPSA. So it's so that is convenient, but it's still expanded quite a bit, and we're currently looking at typically 10 to 20 hours or so until it fully converges. So yeah, that's a ballpark estimate. And I'm seeing all the other questions, and I'll be in touch.
Okay, perfect. So then maybe it's time to wrap up. So first of all, I'd like to say massive thank you to everybody. First and foremost, of course, to all the speakers. I think, we heard a lot of interesting insights about a really broad bandwidth of topics, also different applications from different users and user groups. We're really thankful for all the effort you put into your talks, despite some inconvenient circumstances, for example, incompatible time zones. And I hope that diversity of possible PyPSA applications really serves as an inspiration for future research and other people. Also, massive thank you to all the attendees who really enriched these meetings with their mere attention and also all these interesting questions and remarks. I'm really sorry if we couldn't answer all of them, but there still is the chance to do so in our breakout rooms, which are to follow now. So we have these 3 breakout rooms, and I'd like to share my screen once more so we can see what they're about. So you should be able to see them now. Not this one, this one. So we have one room which should be about the feature requests, which is moderated by Fabian. So maybe, now it's your turn to tell us what would you like to see. Room 2 is going to be about all the country case studies. We had a lot of them, and maybe also some of the questions were left unanswered. So there's maybe another chance to ask them to the speakers or just talk with the general audience about them. And there's 1/3 room about sector coupling and PTX, where I'm going to stay. And yes, you're kindly invited to join.